Is anyone in the Zoom meeting? How many people do we have online? Just let me know. On the Zoom meeting, how many people are online? No. You need to wait a little bit, then we'll start. Um, did you guys get an email regarding course feedback or evaluation or something? Complete it, please. It's very important for us to know how we are doing and then improve the course accordingly. Or if we are doing well, it's very good for us to know that as well. Just complete the course evaluation.
This course?
This course, yeah, you might have gotten an email maybe yesterday. Just double check because I sent out a reminder yesterday night. Okay, so while we're waiting for the other guys, today is probably the most important day of this course, maybe of this degree, because we're going to see attention mechanism, transformers, and essentially all most of the modern AI now is transformers. The good thing is that it is very easy. There isn't anything super fancy about it. Fairly easy to understand, fairly easy to implement. So it should be a walk through the park, but I don't want to start walking until at least a good number of students are here. How many people are online now? 8, 10. Still missing more than a third. 10. Yeah. Assalamu alaikum, everyone, and welcome to the last lecture of the first session of the course. So as I mentioned, today we would look at attention and transformers. In fact, more precisely, we would look at a large language model, GPT-3, would look at its full architecture. Okay, every layer, all minute details, everything, so that we can understand how these modern architectures, modern large language models are constructed, and what is this transformers and attention layer that everybody keeps going on and on about. Okay, so I'm going to motivate it with examples from neural machine translation. So
I think don't share the slide. So
Fine now. Machine translation. Okay, so automatic translation or translation through machines or computer was an important area. Okay, starting from the 50s and 60s during the Cold War time, it was an important research problem to take, for example, Russian and translate it into English automatically. And early attempts were starting to be made in 50s and 60s. Okay, so an important question was, can we automatically translate one language into another? Okay, and up till 2014, okay, the state of the art were statistical machine translation tools. So these were massive code bases which had hundreds of engineers managing it, some rule based, some statistic based. It was like a mess. Okay, it was kind of like from experience, things created on a large scale, required lots of maintenance, lots of updating, and like it would be very difficult for one person to understand that entire mess. Okay, it was some rule based, some language structure based, some statistics based, and so on. Okay, the field changed completely in 2014 with a paper called Sequence to Sequence. Okay, the first author on the paper was Ilya. Ilya was the CTO of ChatGPT's parent company. What's it called? OpenAI. So he was pretty influential in this modern iteration of NLP. Okay. So what was the core idea of sequence to sequence? So sequence to sequence, basically using LSTMs, okay, or RNNs in general. The idea was that if you want to translate a language into another language, what you should do is, for example, I'll take the example of Arabic into English. Okay, so let's take a sentence, Anna. So, Chetan. Okay. And of course, the translation would be, I am very happy. So you take the Arabic sentence. Let's say I want to do Arabic to English. You take the Arabic sentence, you give it the start of sentence, okay, then the next token, then the next token, then the next token. Okay. Finally, until we reach the end of sentence. Okay. And now let's say that if I wasn't doing machine translation example, if I was doing a sentiment analysis example, what would I do? After I have these hidden state representation from all of these states, what would I do? Take the last one, put some loss on it. Okay. But now remember, the task that I want to do is language translation. So I have two languages. I have a language. I have to somehow extract all the information from this language, feed it to, let's say, a decoder for another language and decode it. So let's assume that this is hidden states are H0, H1, H2, H3, H4. And let's say the last state, I'm calling it HT. Okay, the final, because it's not going to be H5 all the time. Some sentences are longer, some sentences are shorter. So now you take this HT representation. This is basically your information from Arabic sentence. Let me write this. It's a RNN, LSTM, whatever you want to call it. Now I have to use this data to get the English statement. So essentially, you can see that you took some information and created a code for it, right? A vector for it. These are typically called in literature encoders. Okay, so this is your encoder block. Now you take your code, the output of the encoder, and try to use it to decode the output. Okay, so you take this h of t, for example, okay, and try to give it start of the sentence, and you see what the outputs are. Let's say this is I. You give the I here. You get M. Give the M here. Very. Give the very here. Happy. You repeat it until you get end of sentence. Okay. This is now an encoder decoder setup. This is what we would want to do. Okay. This is the desired behavior. That on the encoder side, you give a sentence, it's encoded into some code. That code is provided to a decoder. Decoder takes that in, start with the start of sentence, and iteratively decodes the sentence until you get an end of sentence. Now, speaking from an architecture point of view, we can create it. We know how to create such architecture because we have LSTMs. Okay. Now the question comes, how do we train it? Okay, so if I tell you create, and remember, this is now a supervised learning problem. Okay, so you will have a statement in English and a statement, a statement in Arabic, corresponding statement in English, a statement in Arabic, corresponding statement in English. So you will have data sets for it. It's a supervised learning problem. You have X and Y. Okay, but now the question is, how do I construct loss function on it so that I can train it? So these are, I have an encoder network and I have a decoder network. Okay. So what would be the loss function? Okay. Exactly. So basically what Shah is saying is that we would have loss function here, loss function here, loss function here, loss function here, loss function here. Okay. Essentially what we would try to do is we would ask the decoder to output here I, to output here M, to output here very, to output here happy, and output here end of state. Okay. So basically, I is of course the ground truth, right? Let's say that the output was y hat I. This is what the network outputted. Okay, because of course, when you start this training, the network might output gibberish because it hasn't learned to translate yet. It might get some random things, but you will put some loss on it. So you will say, you would have a loss here. You would have a loss on y2 hat and M. You would have a loss on y3 hat and very. You would have a loss on y4 hat and happy. And you would have a loss on y5 hat and end of sentence. And now your job is to minimize the sum of all of these losses. So you will adjust phi and theta in such a way that the output at the decoder is I am very happy, end of statement, end of sentence. Okay. So now you can see if you have supervised data, if you have signals, you will give it English sentence, Arabic sentence here, English sentence here, and train it end to end. That's what's called sequence to sequence. Input to the network is a sequence, output to the network is a sequence, and it's trained end to end. Okay. Everybody's with me? So this is a very strong idea. And this basically changed the entire field of statistical machine translation. And everybody just shifted to this. So the code bases which were maintained by hundreds of people and was very rule-based and things like that. Now it's just some deep neural networks. It's maintained by 6, 7, 8 engineers, could be trained within months, and things became really fast. Okay. So 2014 onwards, the translation tools start becoming way better. Okay, so Google Translate and everything, they were set on. In fact, this method was created at Google. Okay, so Ilya was at Google when they created this. Okay, so there are a couple of points which I need to point out. There are a couple of improvements that needs to be done, but let's start with the first thing. Okay, so remember this setup where we, for example, had sentences, okay, and we given a start word. In language model, we started with a start word and then we sampled from language, right? So you can create, if you have a language model, you can create text by giving the language model a start of sentence or a few words and it would continue the sentence, right? And this is the method that we use to train it. So we give it the desired sentence, okay? And we ask it to produce the token at every instance, every time. So essentially what we did was teacher %. In language models, when we want to produce, let's say, English language, we were doing this. So let's say I want to start a sentence with I am, and I want the language model to complete it. So I would start with, start of sentence, some historic state at time 0. And let's say there is a sentence in my data set, which is I am very happy today. So I would give it start of sentence. I would ask it to produce I. Then I give I here, and I ask it to produce am. Then I give it am here, and I'll ask it to produce very, and so on, right? Until we get end of sentence. That's how we trained. That's how we would train for a language model. In fact, you will do it in the afternoon today, or you will do a character RNN, a character level language model. Okay. And this is a decent idea. This is universally used in training language models. But this might not be a very good idea of in training translation models. Can somebody tell me why? So why can't I? So essentially, what I did was I'm giving certain part of the sentence to my network and asking it to produce the next word. Okay. Why? Because I want it to learn English language. I want it to learn, given a certain sentence, produce the next word. That's the whole requirement in language model. But why this might not be a good idea in translation? Why can't I, for example, give my sentence here, I am very, and ask it to produce the next word?
Maybe another word come in this sentence. I need examples, specific words.
Okay. More importantly, if you think about it, see, in language model, we are learning to model the language. Okay. In translation, we are, of course, we are also learning to model language, but this model is conditioned on the Arabic part of the sentence which is coming. Okay. So if you just give it text here and ask it to produce next word, maybe it would just learn the English language. It would not learn the relation of the English language with Arabic. Because the relation of English language with Arabic is a much tougher problem than the relationship of English word in itself. Okay, so that's why you cannot use just teacher forcing here. Okay, you would have to think of something smart. Okay, and the smart thing is what I have shown here, which is like you just produce the first token, feed it in, then ask it to match the next token, then feed it in, ask it to match the third token. So now the input that I'm giving it, the input that I'm giving to RNN is not from the ground truth. It's not I'm very, it's what I'm producing. But this also has its issue. It might be a bit slow to train. It might be a little difficult to sample. So what we do is somewhere in the middle. So we will, for example, give it some part of the sentence. So some part of the sentence we will give it, I am. Okay. So this, it gets directly from the ground truth. And some part we will ask it to sample. So this is teacher forcing is when you give it the ground truth and ask it to produce the next token in ground truth. This is teacher forcing. Okay. We do somewhere between teacher forcing and complete generation, which is we give it some input and some we ask it to use to sample from its output distribution and feed it in. Okay, this is just some additional information that you need to be aware of when working with translation models. And why? Because we don't want it to learn just the output language. We want it to learn the relationship of the output language with the input language that was fed into it. Okay, so this is a side note. Now let's come to the important part. So 2014, sequence to sequence method came. 2015, there was a major improvement in it with something called cross attention. Okay, so what have we done so far? What we have done so far is that we create an encoder. We get the output of the last token from the encoder, and we use this information in a decoder to decode a sentence. Until we observe and can somebody tell me what is the issue with that? What is the issue with this approach? Where we take a input sentence, compress all its information in an output vector at the last token, then take that output information, feed it into decoder, and reproduce a full sentence in a decoder. And somebody tell me what is the drawbacks? What might be the issue? Order between the words. Okay, this is one point. Okay. Okay, so the question is why? Why should we do that? Why should we? If I give you the task of translation, I don't think people do translation in this way where they read a full passage, then close the book and rewrite the other passage in a different language, right? We don't do it this way. So how do we do translation? If I have to do translation, how would I do it? So what I'm going to do is I'm going to ask you guys to give me an Arabic sentence, so any Arabic sentence, and then I'll try my amazing knowledge of Arabic to translate it into English. So give me like a slightly long sentence. Okay, you have to. Okay. So هذا الدرس مهم جدا للتطبيقات وزارة الداخلية. Okay. So how would I do the translation? So what I would do is I'd read it and then I'd say, okay, I have haza in it. Okay. So this, okay, lesson, okay, muhim jaddan. Now you see muhim jaddan, I will flip it. I'll say is very important. Just tatbiqat. Okay. It's very important for applications. I was going to say for applications in MOI, but both would be fine. Okay. For applications in or at MOI. So now how did I translate it? Okay. I did not just read the sentence one, close the book, and what was I doing? One by one. But not necessarily word by word. I was going to region by region insert it. So for example, in some areas, I changed the order, right? Jid then came before important. Okay. So essentially, what this process is called is attention. So you are attending to different parts of the sentence. Okay. That's it. That's the super idea that changed machine learning in general. Okay.
The word is recognized by the company.
Yes. So essentially what you want to do is you want the ability to attend to different parts of the sentence. Okay. Of course, this would be learned. Okay. I cannot say that go to the first word, then go to the second word, no. It has to be learned. There has to be a smart mechanism for our algorithm to focus on different parts of an input sentence. Now, this can be used for anything. It can be used for language model. When you are producing next word, you might focus on certain part of the sentence. Okay, when you're doing translation, you might focus on certain part of the input sentence. That's basically the method that we need to create today. That's the main topic of today, attention. We want our models to have the ability to focus in on certain parts of the input data. Everybody is with me? Now let's see how we can do it. Okay. Okay, so the setup is clear, hopefully. Okay, so the first thing that I would do is, I would say, hang on a second. Okay, I have to attend to different part of the sentence. What if I attend to all parts of the sentence? Okay, so the first thing that I would do is, I would say that, let me take in all the hidden states. Add them up and feed it everywhere along with the input. Okay, so now the network, the decoder network, not only gets the final state, okay, it also gets all the intermediate states. They're added and they're fed into the network along with the input. So you get the input, which is start of the sentence. Then you get all the hidden states. You can add them, you can concatenate them, it's up to you. Generally speaking, adding is the nicer approach because concatenating would make the vectors a bit long. Okay, so you just add them. Okay, so now this was, by the way, the first thing that we did. Okay, we just simply added them. We said that this history, this can be a learned vector now. Okay, this is G0. We break this connection because we are feeding HT here now, right? So you don't need to feed it twice. Okay, so this G0 is learned, or it can be a fixed vector, whatever it is. And now you produce G1, G2, G3, G4, G5, G6, and so on. That was the first attempt. So what are we doing here? In this part, I am attending to all parts of the input sentence equally. Okay. But I wasn't doing this when I was doing my translation, right? Can I do something better? Can I essentially, you see, the good thing with learning is that you have to define a method whereby you can focus on different words by adjusting the weights of a neural network. Okay, what would be the best way for adjusting these weights? You don't need to worry about it. You will learn it from data. So all I want at this point is a mechanism, okay, whereby changing certain parameters, I can focus more or less on different words. Okay, what exactly these weights would be to allow me to focus properly on proper words is not my concern, because my neural network, my deep neural networks, my transformer networks would learn it. So currently, I just want the ability to focus differently on different words. So now I'm going to leave it to you. You guys tell me a method that comes to your mind whereby you can focus differently on different words. So I'm going to make the problem slightly easier for you. I'm going to say that you have an encoder. You have H1, H2, all the way till HT. Okay. Now you have a decoder. Okay. And at the decoder, you are currently at, let's say, G0. Okay. That's the only information that you have and a start of the sentence. Okay. Now using this information and this information, somehow you have to have a mechanism whereby by changing the weights, you can focus on different parts of the input sentence. So how can we do it?
Neural network, maybe neural network that should approximate what's the importance of each.
Okay, that's a very good starting point. But what would be input of the neural network? What would be the output?
All the hidden states.
All the
hidden states.
All the hidden states. Okay. So what our friend is saying is that we give it all the hidden states. Okay. And we ask it to give some attention weights. Okay. Well, but the thing is, there are a few issues that I can think of. Number one, the hidden states are variable, right? It's not fixed. The neural network would have to have variable length input output. Okay. You can make a claim. You can say that no, I would have a neural network which takes just one hidden state from the encoder and decoder at a time, and then you go over all of them. Yeah. I would say that this is a perfect approach, and by the way, you can use it. But I would start with something simpler. I would say, can I do something just by looking at the values of the hidden state? Okay. Why, by the way, this is a good approach. So what do these histories represent? Histories represent the cumulative information that you have collected from the sentence so far. Okay. So let's say the vector here, let's say you are doing Ana Mansur Jiddan. Okay. The vector here would have information of a pronoun because that's what you have seen so far. Okay. Now let's say at the output, if G is also such that it's looking for a pronoun, then somehow you know that, hey, at this point, I am in a very similar situation as this point. So I need to focus more on this. Everybody's with me? So can I do something with these vectors to focus differently on different parts of the input sentence? Weighted average of what? But how? Okay, I agree with you. So you want H1 to have a higher value, but how will H1 have a higher value? Dot product. Okay, so essentially, if you're looking for a vector which look like this in the input, just take the dot product with all the vectors, and whichever one matches with this most would have the highest value. So you will focus more on it. So the first step that we have done is, we have said that the weight for the first token of history would be G at time t, of course, at the output would be G at time t transpose H at time 1. The weight at time t from the t time, the weight of the input at time 2. Let me simplify it a little bit. I'm taking 2 steps further. Let me make it easier. So at the decoder, I want to have a weight W10 for the first history vector, okay, which is the dot product of the 2 vectors. Okay, at W2, I have G0 transpose H2. W3 would be G0 transpose H3, all the way till WT would be G0 transpose HT. Okay, so simple dot product. I'm just taking G, taking dot product with all of them, and I'm saying that this would be the corresponding weight. Weight 1, weight 2, weight 3, weight 4, weight 5, and so on. Okay. Now, typically, if these vectors are, let's say, d-dimensional, let's take a simple example. Let's say that they are 12,228 dimensions. Okay, that's what we would have in GPT-3. If they are 12,228 dimension, what is the maximum value that you can get from this dot product? Sorry. And let's say that these are 12,228 dimension, but they are bound in between 0 and 1. Let's say they're coming from sigmoid. Each component is a sigmoid is between 0 and 1. No, because it's a dot product, right? So the maximum value at each component is 1, so 12,228. So you can have 12,228, 12,228, 12,228. If you take the weighted sum of these vectors, this can become very large. So somehow, I want these weights to sum up to 1, so that the magnitude of the vector does not grow. I want a weighted sum of my input h's, but I want the weights to sum to 1. So when you have real numbers and you want to do an operation on them such that the output of that operation sums to 1, what do? Softmax. So I'll take these and I'll do a softmax of these. Okay. So I'll say this is exponent of this quantity divided by summation for I equal to 1 to t. Okay. G0T HI. Okay, and I'll do it at all locations. Thank you. I equal to 1 to T exponential G0T HI and so on. Yeah. So I'll just write this as softmax. Softmax. Now you have something decent. Now what you're doing is that at every time in the decoder, you would look at what is the current state of the decoder. You would use this to focus in on different parts of the input. Maybe this one gets a higher weight in the first one, so you look at it more. This one gets a lower weight, so you focus it on less. We know that some of them will get higher weight and some of them will get lower weight because the weights have to sum to 1 and all of the weights are positive. So if you are focusing more on one, automatically you will focus less on another. So now we have a very nice flexible tool of looking at different parts of sentence. Now the question that you should ask is, hey, Naeem, how are you going to fix G's and H's such that you are attending to the right part of the sentence? I would say, I don't need to worry about it. This is the job of the deep neural network to learn. So from data, it would learn that when you are decoding a sentence and at input, the first character was Anna, you have to focus on Anna, pronoun, and you have to get an I. Okay? Yeah.
Now we have it.
Yeah.
And we have G0.
Yeah.
And we have the weights.
Yes.
How can we send different spots?
Okay. Okay, that's a good question. So the question is, okay, you have done, you have the weights, but what are you doing? What is the next step? The next step is that you would, as I mentioned, that you will feed here a summation over I from I equal to 1 to T, weight I of H I. Okay, I'll put a 0 here so that you can say that this is the weights that you are learning at zeros. So now what you will do is you will collect information from all the histories at the input, multiply them with their corresponding weight, add them together and feed it in. So now it knows that I have to focus on I at this particular time. It's doing exactly what I was doing. What was I doing? I first look at Haza. So when it's translating Haza, the weights would be such that it would be focusing on the history vector of Haza. Okay. So at time 0, H1 will get a very high weight. This would be the most important component. Okay. Haza Addaras at this time, H2 will get the highest weight. Okay. Is very, this is H4. At this time, H4 will get the highest weight. Okay. At this time, H3 will get the highest weight. At this time, H5 will get the highest weight and so on. Okay. Once again, I don't fix these weights. These are learned from data. I just give the network ability to focus in on different parts and how to optimally use that ability to do its job. That would be done through data. Okay. Everybody's with me? Okay. So this thing, I think the person who introduces is called Bandani, if I'm not killing his name. Bandani. In a 2015 paper, that basically changed the field of neural machine translation the first time. Okay. This method, this particular method is a variation of attention. It's called cross attention. Why is it cross attention? Because you have the G's from an English language, okay, on the decoder side, and you are using it to attend to the histories of Arabic language from a different language. So it's a cross thing. You are attending from one language to another. That's basically the super idea, which changed the field of machine learning. Okay, simple, elegant, nothing too fancy, just providing the ability to your learning algorithm to focus in on different parts of the input sequence. Everybody's with me? Okay.
Excuse me, Russell.
Yeah.
Here is the difference between the pre-trained model and the pure model. The new one is the weight only.
The only thing is the weights. Yes, yeah.
Is the weight.
Yeah.
So if I got like a model pre-trained with weights, that means they train them in thousands of data sets.
Yes. Yeah.
And if I try to do the same architecture of that model without weights, that give me I need to fine tune and stuff like that. Then they will give me like a big losses, then like not accurate results.
Yes. So if, for example, so let's say we are looking at a transformer, we're looking at GPT-3. Okay, GPT-3 is not open source. Let's say Llama 3. Llama 3 you downloaded. Okay. Llama 3, what Llama 3 has learned is to focus in on the right parts of the sentence, finding these weights optimally. Let's say you fine tune them. Why, by the way, we fine tune? Okay, why don't I just train it with small amount of data? The reason is that if you train it, okay, you don't fine tune it, you let's say you use large training weights, then it would just focus on your weight, try to learn these weights, this new attention mechanism, and your data would typically be a smaller data set, so it would be an overfit. The reason we fine tune it, we say that, hey, we don't have large amount of data. We know that Llama has learned things very well. So what we would do is we would just take what Llama has learned. Okay, let's say these are weight for a particular parameter, and we would just change it slightly. Changing it slightly would ensure that you don't lose what you have learned with Llama. Okay, but that's essentially what we would do. Okay, we would say that, let's say that Llama, they have used 10% of the training data that they used was Arabic. So it's decent on Arabic, but it's not good enough in Arabic for us to, let's say, use it at MOI. And we want to fine tune. So we will collect some data, okay, and we would say, now change these essentially you are getting h of t minus 1, you're getting h of t, x of t, you're getting g of t minus 1, you're getting g of t, and you're getting, let me call it y of t. Okay. So now you're asking them to change p and theta slightly so that the attention weights are better for Arabic. But you don't want it to change too much. You can change it too much if you have large enough data. If you have big data, you can train things from scratch. You can say that, okay, halas, I want to learn them myself. I want my own ability to take GT minus 1 and attend to all the H's. Does this make sense?
Yeah, but I want to train like GT minus 1, the same as we did here.
Exactly.
Yeah.
Okay, but you're training phi to get GT minus 1 in such a way that it can focus on the right parts of the input sentence, of the encoder sentence. Seems like you're not very happy.
No, but I didn't get it.
Okay. Okay. So you see, the G's and H's, these are not learned directly. Okay? These are learned indirectly because the weights of the network are phi and phi. These are the things which you are changing. Okay? But when you change them, basically, what is H? H is basically a method or the output of a method which tells us how to collect information from a sentence. Okay, how do we collect the information from a sentence? We collect it based on theta. The theta will tell it like, hey, focus on these words more, focus on this word less, focus on these combinations of words more, focus on this sequence of words more. This is in theta. This information is in theta. So what you are training for is theta. But because you see, H's and G's are output of the theta and phi network respectively. So when you change theta and phi, you will change H and G. And when you change H and G, you will change the attention mechanism. Okay, you will change the ability to focus on different words differently. Okay. So let's do an example of, like, I want to show you guys, like, is it okay if I use the example of, let's say, language model and trying to to show attention in language modeling and predicting the next word based on the previous words. Same principle. Okay, but I want to show you how attention would help. So let's say example. Okay, let's say I have the statement that I'm trying to work is the tower of London is tower made from stone in the, let's say, 15th century. Okay, let's say that I have the current H states. Okay, so I have, let's say this is one. The first part is, let's say, for stopping words, words which are not terribly important. Okay. Let's say the next word is for tower/building. So if it's one, then it means that it's building. Okay. London, the next location kind of represents places. Okay. And so on. So this would also have tower. Okay. So now when this tower, when you are at this word, okay, and you want to see where in the previous sentence you have to collect the information, you would use this vector to attend to different parts of the sentence. And you will hope that what you have learned is such that you can attend to this location and you can attend to these locations. Why? Because this tower needs to know which tower you are talking about. Okay, if that information is in the sentence, in the previous sentence, it would try to find out. Okay, so it would attend to London and it would attend to this. Then it would be able to produce the next word because it would know which tower it's talking about. So the ability to focus in on these parts, we learn it by adjusting these vectors. Okay, these H vectors, these hidden vectors. And these are, of course, in neural machine translation, these are done indirectly by modifying the thetas and phis. Okay. When we come to language modeling, we would see that we can modify them directly as well. Okay. We can do something directly on the embeddings and try to learn something from it, but that's slightly later part of the day. Okay, so any question broadly on the mechanism of attention? Attention, to summarize, attention is the ability for an algorithm to focus in on different parts of the input sentence. Okay, how we do it is we use the current hidden states, H's, as a proxy of the information held at current state. We did take its dot product with all the previous states or all the previous states at the encoder site. If the dot product is high, it means that this current hidden state at the encoder holds information which I'm looking for. So you will focus more on it. If the dot product is low, okay, it means that it does not hold the information which I'm looking for, so you will focus less on it. How do we ensure that we are not weighting the vectors too much? We take softmax. Softmax ensures that the weights would sum up to 1. So it's a weighted sum of the input sequence, which sums up to 1. And it's, of course, all the numbers are positive. So if some number is high, other numbers would be less or smaller. Okay, everybody's with me? Okay, so at this point, let's take about a 30 minutes break for prayer. When we come back at 12:30, we would start looking at attention mechanism for transformers. We will create the full architecture for GPT-3. Okay, all the bits and pieces, and just get to know all the components. Okay, thank you.
رمضان بدأ
لا والله انا صح لا لا هو اليوم قبل الفجر صح قلت لا اقوم عشان اكل شو الدرس لا غسل ماشي شايف صح نمشي مع شايف تحب ترفض زيك سبحان الله خلاص خلاص لا تقوم لا تقوم لا تقوم لازم تقوم الفجر لأنه في مشكلة دورنا الخطأ والله خلونا نفتح غصب سياسة
طلعونا طلعونا أسوأ ما فيك بدون ما نشوف
تفضل على العين
لأن ما يحدد واحد على الأقصى
سالفة التركي سالفة بعدين علمت
قل له وش نوعك قل له
ما هم عارفين شلون
أنا أبو سيف وهذا الموضوع
سلامك يا رجال وش تسوي انا ما كلمتها خبر قال خلاص طيب لا انا جيت انا طالع عليها احنا طالع منها عشان اسمه يطلع انت ابراهيم معي طالع من ابراهيم سوا والله ما اتوقع اسئله بيطلع نفس الوقت عليكم أول شيء خير قال لي 4 أيام بالدول. طيب في أحد ولا يطلع بكرة؟ يطلع اللي قلت اليوم موجود. ما أوكي بكرة. طيب هذا بعمل صوت أصوات كلها فيها غرامي لا رمضان لا مرة مميز.
ايوه بدأت معك
كيف؟ جوازي. أنا جيت صار أنا سجل في البيت صار شيء ما قصة الوالد تمشي كان عن صار صار لا خيار.
طيب
المفروض يوم بعد جوز ما يعني بس يوم بعد يوم صور وهو نسخة هذا نسخة الجوز الآخر الإسلام يوم بس الحياة إنه خلصوا وقبل واحد ضرب لا مش
ما سويت
لا خلاص مو بالنظام الأول بس
لا لا انت ما تسوي
لا أنا قالوا ما يصير طيب بدي مش فاهم
طيب
ونصور خاصة صور فيه ثلاثة وجه نظر زي ثلاثة كذا واحد نعم يوم الخميس بتركيبين يطلعون يوم التكشيف من الظهر يوم جمعة دوامة طلع مسألة الجمعة
شوف دي مسألة
خاصة كيف طلع يحفظ موجود وقت اللي ما أساسا كذا كان شوية ما بكر يسمى بعض المطاعم كذا وطلعت شوي ما صور بس صور عندنا خاصة من الطالب
ما ذاك رقم طلب سالب
هذا انت ترتيب بس حاول بها
زين
الحمد لله والله ابراهيم هو بس جدا الخاص ممكن انا اتوقع كده بتعيش تقريبا بسم الله عارفين هذا
متى ممكن ينزل لو ما حصلته يقول والله جاء حد أخذ مسافر ما حصل بس طابع أكيد ما تخلي عشان ما ياخذ احتمال كيف الأمر كيف
بس خمس ساعة خمس كويس خمس ساعتين ساعة
طيب الجلسة سنس كيف سبب هنا ولا معنا؟
اليوم بس
خلاص نتكلم طيب طيب
ساعة
أمس
مش كثرت هذا النص
أمس أنت أنت أمس
لا أقول بالله نص فلاش أخبار مسؤولية أو بزكاة عين تطاوس كثير من المنظمة شو كان قصة
صوت شوي.
لا عشان مثلا خسر الوقت زيادة كنت بس مش مفلوس.
طيب
هو القطع ولا
لا أنا يوم
وزاد خناقة إذا هو هي أنا بس ما تسكر
40 ثانية
So they mentioned 2000.
220.
What do you mean by this?
Embedding, that's embedding. We'll come to it. I will explain. Okay. So H, it's the vector which is to capture all the history. How many component it has? It's 12,228 for GPT-3.
لا بس انا اقرا شباب انا بسيط يعني صغير ترى يعني صغير والله يمكن تعرف كذا في ميدان السوق صح؟ تشتغل بالمكتب اللي قدامي اذا تنمر عليك والله هو شغال انا صح من المكتب من الدريس كان عندي دريس بس مكتب المكتب اللي قدام السباق
Okay, guys. Guys, can we get the rest of the people in? Let's start.
Yeah.
Guys, okay, Shabab. Shabab. Guys, let's settle down. Thank you. Thank you very much. So let's resume. So before I move over, I just want to make a few additional comments regarding RNNs and LSTMs. So so far, the architecture that we had seen was vanilla, i.e. we had one layer. Okay, which we apply recursively to data. Okay. There might be cases where we have more than one layers. Okay. For example, we can take output from here, feed it into a second layer. And so on. And you can add a third layer and a fourth layer and a five layer. I think 5 is kind of the upper limit for adding layer to RNNs and LSTMs. Okay. With increasing number of layers, of course, the learning capacity would become better up to, I think, 5 layers. That's one thing. So these are multi-layers. Multi-layer RNNs. Okay. Another thing is that there might be, so far, what we have done in RNNs is that we have information flow in one direction. Okay. So we flow in this direction. We start from H0, we get X1 with H0 and X1, we get H1 and so on, right? So we have information flow. Okay, but by the way, nothing is stopping us from having information from the other direction as well. Okay, where will be the application where we have, for example, application information flow in the other direction? So if you're doing language modeling, of course, you are only going in one direction. Okay, you're predicting the next word and the next word and the next word, so you're just going forward. But when, for example, you're doing language translation, the Arabic text that you have, which you are translating to English, you can go in it both directions because you have the sentence, right? You have the right to go in either direction and collect information from it. So you can have bi-directional RNNs as well. So bi-directional RNNs have information flow in either direction.
Encoders only.
In encoders only. Decoder you cannot because you don't have future. Okay. So these are called bi-directional RNNs. So these are just some additional information on RNNs, multi-layer RNNs and bidirectional RNNs. Okay, so now the current trend that the field is going in, it's basically independent of this recursive relation of RNN. So this started with 2017 paper from Google, which was attention is all you need.
So Professor, we're talking about translation only, one-to-one word. We're not talking about something has information, like we're asking a question and getting answer.
Asking a question and getting an answer is language modeling. Okay, so how do you do answering, asking a question and getting an answer? This is a language model. Essentially, you'll have a large language model, which will have some question. You can even give it some prompt. Okay, and then you give it the start of the answer, which is start of the sentence, and that's it. Based on the prompt and the question that it has seen, it would produce more information. Question answering is language modeling. Does it make sense? So the 2017 paper, attention is all you need, essentially said that attention is a strong enough tool for you to ignore that recursive pattern. Okay, so if and there is good intuition to it. So basically, what was this recurrence in recurrent neural network is that we were, each one had the historical information of the sentence up till time 1. H2 has the historical information of the sentence up till time 2. H3 has the historical information of the sentence up till time 3, and so on. Now, if you have the ability to attend to different parts of the sentence anywhere, why would you need to compress that information in one vector at HT? You can go to all the historical times anywhere. Whatever was the important information, you can collect it. Does this make sense? Okay. So what I'm saying is that rather than accessing all the information, is the speaker working? Can you guys? Okay, it was off. So rather than getting the historical information through one vector, H3, at any time in the decoder, because you have the ability to attend to all historical informations anyway, you don't need to compress that history. So what attention is all unique paper says is that you don't need these recursive connections. Okay, what you can have is, you can have an embedding for X1, an embedding for X2, an embedding for X3, an embedding for XT. And with attention, you can, let's say you have a decoder Y1, you can attend to different parts and extract useful information. Okay. This basically changed the way we do NLP. Okay. Because this now attention is actually all you need in NLP. We just use attention most of the time. All the state-of-the-art tools that that we are using in NLP, these are based on attention now. Okay, so let's try to see how this idea changed the world. So let's look at language modeling, okay, because language model is the key field, the key area that we are, for example, question answering is just an application of language modeling. Okay, summarization is an example of language modeling. Okay, let's say some essential feature extraction from document, it can also be done as a language model application. So how would we do it? So essentially, in language modeling, we were interested in probability of x at time t given x at time t minus 1 all the way till x1. Okay. Now with attention, the way we would handle this is that we will have x1, an embedding for x1, okay, x2, an embedding for x2, x3, an embedding for x3, all the way till an embedding for x of t minus 1. And essentially, you would take this embedding for x of t minus 1, and you would feed it into some neural network to give you a distribution on probability of x of t given everything less than x of t minus 1. Of course, for this to happen, this embedding has to have information from everything in the past. Okay, it needs to look at the entire sentence to be able to produce the next word. And to do that, we use attention. So we basically say that this embedding would have the ability to look at everything in the past, collect information, propagate it forward, modify this embedding such that this embedding can now be used to produce the next word. That's basically the core idea in GPT-3 or GPT-based algorithms. Okay. Everybody is with me? Okay. So think of it like this. And by the way, the good thing is that, let's say this word is, I'll take a word in 2 sentences. Okay. So I take a sentence which is today is Monday. The next day, let me just stop at the next. Okay. And this is next sentence I will do is this month is Ramadan. the next. Okay. Now the word the next is the same in both sentences, right? So the embedding for next would be same. Okay, but in this sentence, the first sentence, the next word or the sentence would be completed as today is Monday, the next day is Tuesday. Okay, and in the second sentence, this month is Ramadan, the next month is Shawwal. Okay, how do we keep track of these different situations? So you will have an embedding for next. The embedding for next will collect information from embedding from all the previous words, okay, to try to modify itself such that it can predict the next word. Okay, so you have essentially, let me like this. So attention layer and transformer takes an embedding for each word, x1, x2, x3, all the way till t minus 1. Okay. And it gives you a new embedding, okay, where this embedding is some modification of, I'll call it x of t minus 1 tilde, okay, and it'll give you x1 tilde and x2 tilde and so on. So in the first sentence, the embedding of next would be modified such that when you feed it to the neural network, it would predict the next, it would output the next day is Tuesday. In the second sentence, it would predict the next month is Shawwal. Okay, everybody's with me? So essentially now you're working with embeddings, word embeddings, and you have to learn some modifications of these word embeddings such that these modification captures the context and allow you to predict the next word. All good? Everybody's with me, by the way. Any questions? Okay. If not, then let's proceed. Let's try to set up this and try to see how we can proceed. So let me just show you guys some concepts which are which we will go through. Yes.
What is not done before, it's just the hidden states that has been removed.
Exactly. So previously we were iteratively capturing history. Okay, because that was our understanding that that's the best that we can do. With attention, we are saying that because you are attending to all the words anyway, whatever history is important, you will capture it with attention. So you don't need to do it recursively.
So how does that enhance the, I mean, computationally, it was enhanced, but in terms of how good the model is, how did it?
Okay, so what was the issue with recurrent neural network based architectures? So we saw that because it's an iterative method, you have the issue of vanishing gradients. You cannot go over larger context. The issue is that with transformer, you don't have the issue of vanishing gradients. Okay, you will see that we'll have a very easy skip connection. Okay, almost everywhere. So gradients are very well defined. You can have as deep transformers as you want. The second thing is you had this hard constraint that whatever history, so essentially imagine that in the sentence, you have some word which is important for 10th word, but it's not terribly important for the second word. But because you are doing things iteratively, because it's needed at the 10th time, you would have to carry it 2 times 2, 2 times 3, 2 times 4, 2 times 5, 2 times 6, all the way to 10 10. You understand? In attention, you don't have to do it. If attention, if it's important for the 10th word would look at the second word and get that information from it. So you have the ability. So think of it like this: like if I ask you that you are in a building, okay, and you have the option of going through an elevator where the elevator will stop at each layer, each level, and in the other one you have the option of taking the elevator to any level that you want. I'm quite sure that all of you will take the second option, because recurrent neural network essentially is stopping at each stop to collect the information. Okay, and it has to carry that information all the way through. Okay, whereas in, attention, can jump to any point in the network and get the relevant information for itself, independent of other words. Okay. So this is basically this is from the 2017 paper. Okay. So attention method, you can have an encoder decoder setup, for example, language translation. This is what it is. This is encoder, this is the decoder, or you can have it just in the decoder setup, where, for example, producing next language. So LLMs, GPT-3 is just this part. It does not have an encoder. Okay, it's just a decoder. So let's first just look at what do we have in here. So we have some embeddings. Okay, then we have some positional embedding. Then we have multi-head attention. Then we have addition and normalization. Then we have a feed-forward network. Then we have a linear layer and softmax. So we have to go through all of these, and we need to understand what these components are. So I've written them here. We have tokenizations, you have input embedding, positional embedding, query key and value, attention, self-attention, multi-head attention, feed-forward. We'll go through all of this. And this basically combined together is basically any modern transformer-based architecture that we have. Of course, this was GPT, up till GPT-3. The more modern transformer architecture have minor modifications of these. Like, for example, it might have an efficient caching for a key query value and so on. It might be a little bit better in positional embedding, positional encodings and so on. We will look at it in the next thing. But in raw, this is the general structure for a transformer. Okay. So let's try to see what these things are. So first thing, that I want to do is I want to define the two types of attention that we have. So attentions have cross attention and self attention. Cross attention is what we saw in translation. Okay, where you have an encoder and the decoder is attending to encoder. So it's one language attending to a different language. And self-attention is something like language modeling, where you have one language and you are attending to different parts of this sequence line. Okay, so GPT-3 uses what? Self-attention. Okay, so we would look at self-attention in detail and try to figure out what we do. Okay, so the first part of any large language model would be tokenization. Okay, I will define it at the end. Currently, for us, tokenization is just 50,000 words that you have in your dictionary, or 60,000 words that you have in our dictionary. In the case of GPT-3, we have 50,257. This is our vocabulary size. Okay. So the first thing that we have to do is we have to learn some embeddings for words. So each word, we want to represent it by a vector. Okay. So in transformer-based architecture, these embeddings are learned. Okay. So what you will have is, you will have the first word in the vocabulary, the second word in the vocabulary, the third word in the vocabulary, all the way till 50,257th word in the vocabulary. And you would learn a vector for each of these, an embedding vector for each of these. I will call that EV1 all the way till EV 50,257. Okay. The dimensionality of this vector is 12,228. Okay. How would you learn it? It's basically just some parameters. Okay. You would say that each word, you would learn a corresponding 12,228 dimensional vector for it. Okay. How do we learn it? We don't need to worry about it. We learn it through backpropagation. Okay. So you asked the question, how would the vector for queen and queen be similar? It would be similar because that's what the data would ask it to do. Okay. Data would ask it to do that, to learn it in such a way that king and queen would be similar in almost everything other than gender. So this is learn. This is the first thing. Okay. Now the second important thing is that in recurrent neural networks, we had some information of the position of a word in a sentence. Why? Because you are going in a sequence. You're going from word 0 to word 1, word 1 to word 2, word 2 to word 3. So the position was implicitly coded into this algorithm. Okay. Attention is an operation from set cross set onto real numbers. So attention is basically if you have two sets, okay, it's an operation from these and you get real number, which is as time is. So if you have, let me explain what I'm saying. If you have, let's say, 3 words, I am happy, each word can attend to each word and get a weight. That's basically attention. Okay. So this word can attend here, this one can attend here, this one can even attend to itself. Okay. Similarly, this word can attend here, this one can attend here, this one can attend to itself, and so on. Okay. So what would happen is that you would get a 3 by 3 matrix. Okay. Now it doesn't have any notion of position. If you, for example, change the position of M here or here, the output would be the same. But we know that in sentence position is important. Okay. For example, I am happy, not sad. I am not happy. I am sad. So the only thing that changed in this sentence is the position of not. But attention mechanism, it would get the same answer for both these cases. So somehow we need to add the positional information with the embedding. Okay, so multiple things can be done. You can, for example, take the embedding of the word and add some embedding, positional embedding for that word. Okay, so if that word is at position 1, you will add the positional embedding of location 1 here. If that word is at position 2, you will add the positional embedding of position 2 to that word. If that is at position 3, and so on. Okay, you can also, by the way, concatenate. But concatenate, as I said, not a good idea because it increases the sizes of your vector. So what we do in typical transformer architecture is we add things. So now I have a question for you. What can you use for positional encoding? What can you do to encode the position of a word in a sentence? I'm sorry? Okay, we use sine waves, but can you tell us why this is the case? But many things can be periodic. For example, a square wave is a periodic wave. Okay, so let's first see what do we want this positional embedding to represent. Okay, so this positional embedding has to have a unique vector for each position. Why? Because we want to use it to tell different positions apart. Right? If, for example, if I say that, okay, the positional vector for all positions is just a vector of 1s, then there is no point in adding that, right? Because it would not convey the information of the position. So what we need is we need vectors which are different for different positions. Okay? So the best way to do would be if we have some sort of a unitary matrix, which is like, if you take the dot product of each positional vector with itself, it gives you an answer 1. If you take its dot product with another position, it gives you 0. That would mean is that these vectors are totally different from each other. They don't have any projection on each other. Okay? The only projection that they have is onto themselves in this vector space where you have these positional embedding. And these are limited to a magnitude of 1. Okay? That's basically what these sine waves give us. Okay? We don't need to go into too much details. Essential idea is that I have to have positional embeddings which can capture positions of unique positions of words. As such, they should not have any projection onto each other. Okay, and that's what sine waves can do very effectively. So if you have a sine wave, okay, and then if you have a sine wave of double frequency, okay, the projection of the two waves onto each other is 0. Okay, and you can very easily see it. You can very easily see it that if you take the integration of the product of these two, the product of these two is positive in this region, the product of these two is negative in this region with the same amount. It will cancel each other. Okay. The product of these two is positive, and the product of these two is negative in the same amount in this region, so it would cancel each other. So the projection of these two onto each other is indeed 0. Let's look at the projection of the red wave with the green wave. So if you multiply red or green, because these are symmetric, essentially the output would be like this. Negative, negative becomes positive. And then if you take the integer of it, it will have a value of 1. That's why we use cosines and sines. I think that's enough for our use for this class. Okay, everybody is with me? Okay, so we need embedding of a vector. Okay, embedding is an operation from set to set. It does not have any notion of position. So we have to add something to include this notion of position. And to do that, we added positional encoding. Okay, everybody is with me? So now we have a good encoding for our input word. So if
trying the microphone.
لا عندنا مشاركة رياض تصلي الحين بدري تعرف.
So it seems that Ramadan has thrown off everybody's. Now, I had a feeling that there would be very little difference, but even I feel a little bit dizzy when I'm teaching, so I can understand that it might be a little bit.
He is lucky it's not another player.
Because then, yeah, people will be. So I'll tell you a small anecdote. So microphones were very new, and like when my father was young, and he was like, he was interested in religion, so he spent some time in the mosque. So in at that time, the clocks were not very common. It's probably 60s. So he would make an announcement that the time is approaching, because to speak of summer, 60s was, and people have to work in the farm. So you have to time it exactly correctly to drink water right when you close the fast and when you open it. So he would make the announcement. So because he was studying in university, so he said it in a very like refined Pashto. And the word for this is nosh, which is very close to no. So he made the announcement that it's time to drink water, and people took it to not drink water. So everybody was like, it's like, why? Anyways. Okay, so we have the embedding set. Okay, so we will learn an embedding, and then positional embedding. Remember, we are not learning in this case. Okay, we have fixed vectors for it. But you are, by the way, allowed to learn positional embeddings as well. Okay, so you can have a matrix for learning word embedding, and then a matrix for positional embeddings as well. But in general, most cases, people just fix the positional embedding and use it just in an additive way. So we have fixed the embeddings. So you will give me some words, x1, x2, all the way till x t minus 1. Okay, I will get the embeddings for them. And I will add the positional embedding for them.
One question.
Yes.
For the positional embedding, when the vector has its weights, okay?
Yes.
When we do concatenating, we're adding extra vector below.
Yeah.
And we know it's assigned for one purpose, which is positional.
Yes.
But when adding it directly, is that will add some noise to the original?
That's 100% correct. It will add some noise. But the good thing is, because we have added a very nice periodic structure to it, you can extract it. So if, for example, you give me an embedding and you say that I have added a positional embedding to it, find me which position it was, I can recover it. If I can recover it, the neural network can recover it as well. Okay, that's why we are looking for unitary things, because essentially, why am I adding the positions? In fact, what I want is I want my network to have the ability to see where it is picking this information from. That's it. All it needs to know is how far away is the word which it's currently looking at. Okay, embedding itself does not tell it anything. It's just a dot product. It's an operation on set. Set has no order, right? Elements are in no order. But if you have this position embedding, then you can very easily capture where the position. And that's why we are looking for unitary metrics. We're looking for periodic things and so on. Okay, so people thought about it, and that's why they are using it. But the short answer is that if you give me an embedding, okay, and it has a positional embedding added to it, okay, for some position I can find out what this position I is. Even if you don't tell me what it is, you just give me the total. You just give me this. Using this,
Mathematical approach to
exactly,
visibility.
exactly. Okay, I can do that if I know what is the lowest frequency that you're using. Yeah. I'm sorry.
Is it by sign numbers?
No, it would not be trivially easy. It would be like you would have to do some thinking for it. Like, but it can be recovered. Like it's an invertible operation. Okay, so okay, this part is done. Now we have the word embedding and information of a position added to it as well. Now comes the job of attention. Okay, how do we attend to different parts of the sentence? So you have the embedding vector at time t-1. Let's say you want to attend to all the previous embeddings. How would you do it? We have already seen it. This would be the exponential of embedding at time I. Embedding at time I transpose, embedding at time t-1. Remember, dot product is a symmetric operation. So if I write et-1 transpose ei, or if I write ei transpose et-1, both are the same. Okay, divided by summation over I equal to 1 to t-1. Okay, eit and et-1. Okay, this is the weight of the ith token to the t-1 word. Okay, and it's very easily implementable. You're just taking dot products, you get the real numbers, you take the softmax of it, and it tells you how much weight you have to. Now, how will I collect the change in embedding? The change in embedding delta E would be summation I equal to 1 to, let me, for sake of ease, let me do it till t-2. Let me not take the change in embedding from myself for now. Okay, so I'm looking at all the previous times, okay, not on the time itself. So from I equal to 1 to t-2, wi at t-1, embedding at I. That's the change in embedding. That's essentially, I'm using this embedding to look at all the previous embedding and then collect the relevant information from it and add it here. Yeah. Now, when I'm armed with this change in the embedding, I can do E at t-1, E at t-1 plus delta E at t-1. I can use this, feed it into a neural network to predict the next word. Okay. But this is just one attention layer. And you know that language is way too complex for one attention layer to do everything. So we, of course, need multiple attention layers. We need multiple heads. Now I'm going to explain all of this. Okay, so let me start with first thing first. The first thing is that if I imagine that, let's say, some embedding at time 2 is giving me some information at embedding t-1, okay, or embedding at time 3 is giving me some information for embedding at t-1. Typically, one word cannot give you information which would span over 12,228 dimensions. Okay, one word is not going to change everything. One word might change a few things on your vector. It might change maybe 10, 5, 15, 20, but it's not going to change 12,228 dimensional vector altogether. Okay, so we want to restrict these changes in some low dimensional space. Of course, I don't want to fix it. I don't want to say that T1 will change the first component. and E2 will change the second component. So I will learn it. I will learn some low dimensional space where these vectors will make changes. Why, by the way, I'm, by the way, perfectly entitled to do these changes in this high dimensional space. But if I'm doing changes in this high dimensional space, then I have to do dot products in this high dimensional space, okay, which is expensive. Okay, one word is not going to have change spanning over 12,228 dimensions of my vector. So the key idea that we use is we say that, okay, we are going to take this 12,228 dimension vector and project it into some low dimensional space. Okay, look for similarities and information transfer in this low dimensional space, then project it back up. That's the idea. So what I say is that rather than taking the dot product of embedding vector at time t-1 with embedding vector at time I, can I do something more efficient than this? Okay, because of course each word would convey some information, not all the information. So to do that, what I say is that I will project this word into some low dimensional space. Okay, how would I do it? I will take the embedding vector. So remember my embedding vectors, I have drawn them as row vectors. Okay, so if I want to project it into low dimensional space, this would be an embedding times a W. Okay, this W would have number of rows in this W would be something like 128. Okay, so from you take in a vector which is 12,228 dimension. Okay, you multiply it with a W which is 12,228 dimension times 128. So this vector would become a 128 dimensional vector. And dot products of this 128 dimensional vector, of course, would be cheaper than dot product of this high dimensional space. Okay, this is one thing. The other thing is, if you look at this operation, if you look at this operation, the attention from ET-1 to E1, this would be the same as the attention from E1 to ET-1, because dot product, as I mentioned, is symmetric. But this is not necessarily true. Okay. For example, the information that month will convey for Ramadan is different from the information that Ramadan will convey to month. Okay. So if you want to modify the embedding vector of month, and you know that there is a word Ramadan, so you might want to say that, hey, these months are Islamic calendar. So you might want to modify this information. It's not Gregorian, it's Islamic. Okay, but if you want to change the information of Ramadan from month, you might want to change, for example, that this is 9th month. Okay, and so on. So the information that flows between two embeddings is not symmetric. Okay, particularly in language models, but here it seems like it's symmetric. So how can we fix it? How can I modify this operation such that information from E1 to ET-1 is not the same as information from ET-1 to 1? Okay, so this dot product is symmetric. Okay, so the weight between ET-1 and E1 would be the same as the weight between E1 and ET-1, because this dot product is, if you change the position of these two, it doesn't change. But what I'm saying is that in data, this might not be the case. Okay, for example, I gave the example of month and Ramadan. Ramadan and month might not depend on each other in similar way. Ramadan might want to extract some information from month, month might want to extract some different information from Ramadan. So we want the ability for this dot product to be not symmetric. Okay, and now I'm asking you guys to come up with some idea, some solution where I can have non-symmetric behavior here.
Since before we have positional encoding, then there will be a difference.
Yeah. It would be a difference of position, right? But not the difference of word. Okay, because of course, yeah, you know that these two have different positions. Okay, that much we know, that these are located at, this one is located after it, or this one is located before it. But even with that, we would want different type of information to flow between the two. For example, in the context of a sentence, let me think of an example. Okay, where one word is important for the other, but the other word is not important for the first one. Okay, let's take the example of the Tower of London. Okay, so the Tower of London, tower would depend quite a lot on London, because London tells it which particular tower we are talking about. Okay, but London might not worry too much about the tower. Okay, because remember, in the context of this sentence, tower is the thing which, so London would, tower would depend very heavily on London. So the tension between tower and London might need to be very high. The tension between London and tower might not need to be that high. So I need the ability for this attention operation to be asymmetric rather than symmetric. And I'm asking you guys how we can do it. Okay. So what I'm going to do is I'm going to
Maybe we add some constant that's before the vector might distinguish between
okay.
the relation.
Okay. So the answer is on this slide. Okay. Query key and value. Okay. So what I'm saying is that I would not use the embedding to collect weights or attention directly. What I will do is I'll use the embedding to get three things. I will get a key, I'll get a query, and I'll get a value. Okay. Query basically defines what information this embedding is looking for. What is the question that this embedding is asking? Key is the information that this embedding is providing. Okay. And value is the information that it will pass on. So now the two words, for example, the tower can ask a question like, hey, do you guys know my location? And London would have a key which would say, I have location. So when the tower asks, do you know my location? London would say, yes, I have location, and the location would be passed. Okay. But London, for example, might be asking like, which context am I being talked about? Okay. The query, the key of the tower might not have any information about it. So it would not attend to tower. It might attend to something else. Do you now understand? So we create, rather than using this embedding, we created three vectors. A query vector, which is the information that I am seeking, the embedding is seeking. Key vector, which is the embedding, which is the information that I am providing. Okay. The questions that I'm answering, I'm sorry. Okay. And the value is the information that I will actually propagate. Okay.
To answer a particular query, I will use the key to get the value.
That's exactly what. Okay, so Shai has done a much better job than I was doing. To answer a particular query, I will use the key to get a particular value. Okay, thank you. So now the question is, how do we get the key query value from embedding? Okay, these are simple linear transformations. So the embedding is multiplied by W query to get the query. The embedding is multiplied with W key to get the key. The embedding is multiplied with W value to get the value. Okay. Now there is an additional thing that I mentioned. I said that an embedding is not going to change all 12,228 dimensional space. So what we do is we say that we will work in some low dimensional space in this embedding space. So what I'm saying is that we have 12,228 dimensional space. But the changes that I'm going to make are going to be in some 128 dimensional subspace in this. Okay. And again, this is learned. Okay. So we are learning this from data. Okay. And why, by the way, this is a good idea. So think of it like this. So in one particular attention, okay, I might learn that for this data set, information of places is very important. So this particular key query value pair would learn to make changes for locations. Okay. For another attention, I might learn that the information of time is very important. So that particular key query value pair would learn to make changes in this 128 dimensional space for time. Another one might learn to do the same thing for say gender. And so on. Okay. So that's what these different attentions are doing. And these different attention, by the way, are called different attention heads. Okay. So you have different heads. Different head means that you have a key, query, and value for this head, which is looking for particular changes or particular flow of information from different words in the context. Everybody's with me? Okay. So this is 128 dimensional. This is 128 dimensional. This is 128 dimension. If you are making changes in 128 dimension, you of course have to learn which are the 128 dimensions in which you are making the changes. You would have 128 vectors. Yeah. So typically this is denoted by an output vector. Okay. Which basically defines the 128 directions in which you are making the changes. Yeah. So let's try to set up an attention layer now, a multi-headed attention layer now. So a multi-headed attention layer will have this. So multi-head attention layer would have a query, a key, a value, and an output matrix. Let me call it 1. Then it will have another head, which will have query 2, key 2, value 2, and O2. Then it will have all the way till in the architecture for GPT-3, we have 96 heads. Q96, key 96, value 96, and O96. So you have these 96 attention heads. Okay. So now look at this, the ability of these different heads. So tower in different contexts might want to ask different information. For example, tower might ask, hey, do you have any information about my location? Tower might also want to ask, hey, do you have any information if I'm fictional or real? Do you have any information of when I was built? Do you have any information of where I'm located? Do you have any information of which material was used to build me? So these different heads are used to ask these different questions. Everybody's with me? How are the questions asked? The questions are asked with query. The questions are answered with key. And the value that is passed on, the answer that is provided is the value. O vector is used to change this 128 dimensional vector back into the projection of the embedding space. Okay. So now let's look at the architecture that we have seen so far. So we have, remember for, we said that for GPT-3, first we have an embedding layer.
You said there is lastly projection from 128 to
Yes.
12,000, the full.
Yes. Yeah. Okay. Why? Because you see, you are saying that make change. You will give 128 vectors and you will say change the first vector by an amount 0.2, change the second vector by an amount 0.3, change the 128 vector by an amount 0.5. But what are these vectors? Because I want to change the embedding. So you will take these 128 changes, multiply them with these 128 vectors and get the change for the full embedding added to the embedding. Okay. So let's see. So in embedding layer, I said that my vocabulary size was 50,257, and each of my embedding was 12,228. So can somebody do this multiplication very quickly and tell me how many parameters are? So GPT-3 has around 175 billion parameters. Okay. So I want to account for each one of these. I want to figure out where these parameters are used. Okay. Okay, so I'll say roughly 615 million. Yeah. So this is less than 0.5% of all the weights of my network so far. Okay. Now let's look at multi-headed attention layer. Okay. Remember, in multi-headed attention, what am I doing? I'm multiplying the embedding with WQ. I'm multiplying the embedding with W key. I'm multiplying the embedding with W query. And I have some output vectors, which is, let's look at the shape of all of these. So what is the shape of W? It's taking 12,228 dimensional embedding and converting it into 128. So this is 12,228 times 128, right? Again, same thing for E, 12,228 times 128. Same thing for, this is very good, 12,228 times 128. And again, the output vector is, it will take 128 dimensions and project them back into 12,228. Okay, so I essentially have 12,228 times 128 times 4. Okay, this is for one head. And as I mentioned, I have 96 heads. Okay, so can somebody do this calculation? No, it would be like multiply by 96 as well.
600 million.
Okay.
For the embedding layer, I think it's around 300 million, not 600.
Okay, just give me 1 second. So you have 600 million, and then you have around 96 of these layers. So this is one multi-head attention. You have 96 multi-head attentions in GPT-3. So can you multiply it with another 96?
Even with the multiplication of 96 on the left, so another 96.
Yeah, this is one layer because each layer has 96 heads. Then you have 96 such layers as well. Okay, 57 billion. Okay. Let's use 57. Okay. So you have, like I said, 175 billion. 57 billion is roughly 1/3 of that. So we have accounted. I was going on attention, and attention is only 1/3 of the weights of your transformers. So where is the rest of the weights? Okay. So let's try to answer this question. So you see all the operations that we did, these are very neat. Okay. So we did this. We said that output from an attention layer is input of an attention layer plus summation for all the words from I equal to 1 to t minus 1. Weight for that, let me call it t minus 2, the same thing that I was using. Weight at I. By the way, I was trying to avoid taking the weight of attention to itself because I had embedding vector, and taking the dot product with embedding vector might not be correct answer. But if you have key and query, now you can do it. Okay. So for example, let me explain this. So let's say that let's take the example of the tower. Okay, tower is asking, I'm currently at a word. Let's say the tower is located in a cold, dry country. Okay, so now I'm at, let's say cold, dry country is a token. Okay, so now, okay, so what I'm saying is that my current token might be asking a question, might have a query, which I can answer by using some other embedding in this. So for example, cold, dry country might give me some information about the place that I am in. Okay, of course, it does not tell me where I am exactly, but it can tell me most likely that I'm not in Saudi Arabia. Well, you can be in Saudi Arabia, January, but like I'm not in a desert. Okay, or let's say that it was said that northern hemisphere. The northern hemisphere is not telling me where I am exactly, but it's telling me at least some information of where I am. So what I'm saying is that these components, different components of embedding vector, some component might be able to pass information to a different one through the key query pair. So now you can self-attend as well. So you can have this at up till t minus 1. You don't need to be up till t minus 2. Wi times the embedding at I. Okay. This is from a single head. What do I do if I have multiple heads? You just do another summation from j equal to 1 to, let's say h, which is h is the number of heads, and then you do wij and eij. Okay, that's essentially a multi-head attention layer, what it's doing. Okay, so it's collecting information from all the embeddings, okay, and creating something nice where I can predict the next word if it's language modeling. Now I have a question. Okay, these are vectors. Okay, E is vector, this is vector. This whole change, I can write it as E plus delta E. What is the limitation of this? This is a vector addition. What is the limitation of vector addition in this particular case? No, think of it from information propagation point of view.
What would happen if we add together?
Yeah, we can add together. The operation works fine. But there is a limitation of this type of vector addition in terms of information propagation.
We will mix the data, so we will mix the information, so we don't know. It will not be mixed, it will be aggregated.
Okay. So Shah is saying that we mix the information. I would take a slightly different approach. I would say the limitation of this is that different components of the vectors do not talk to each other. Okay, so what you're doing is you have a vector E. It has some values. Okay, then you have some delta E. Okay, so this is E, this is delta E. And when you do vector addition, this is added with this, this is added with this, this is added with this, this is added with this. But these features might have some information to talk to each other as well, right? They might have some information to pass on to each other. How do we do that? How do we allow them to talk to each other? This component to talk to each other. For this, we have fully connected layers in Transform. Everybody is with me? Why do I need fully connected layers? Because I'm collecting information of a feature and I'm adding it to this feature. Okay, but this feature might want to talk to a feature in 96 location. Share some information, transfer some information. I don't know what they talk about. Okay, but I want them the ability to talk to each other. If it's important to talk to each other, they would learn the weights accordingly. But like I said, in machine learning, we want our algorithm to have the ability to do a certain things. How important or unimportant that is, you can learn it during training. So now what I will do is, I want to take this. Yes. No. So you added, you have done the attention, you have take E, you have added delta E to it. Now after that, I'm adding a new layer. The new layer is that I took this is E plus delta E. Now what I would say is that I want these things to talk to each other. Okay? For them to talk to each other, I would say that I will enter them into a neural network, where the neural network would have 12,228 inputs. It's a one hidden layer neural network. Okay, yes. So this would have, the hidden units is 49,152. Okay, and output again is 12,228.
If we applied neural network in order to mitigate the addition problem.
Yes.
Why we are doing this? Why would we not concatenate the two units and try to output one?
No. Okay. So the question that Mohammed is asking is that, okay, I understand the limitation of attention. Attention, the limitation is that different features cannot talk to each other. Why don't I take embedding, the change in embedding, okay, and pass them through a neural network and learn something. This can be a valid approach. The approach that I'm taking is, I'm saying that attention, each feature, so you are looking at a feature, which is, let's say, a feature of place, and you are collecting its information from all of the history. Now you have collected this. Now you have the updated information. Now you want to see that in this updated information, can features help each other a little bit? So for that, you pass it through now fully connected layer. It's basically two fully connected layers. It's a small neural network with two layers. Okay, so this allows, because it's a fully connected layer. So this node is going in here. This one is going in here. This one is going in here. This one is. So they talk to each other and then they merge their information, share their information. So let's try to see what is the weight of this particular neural network, fully connected layer. So this is 12,228 times 49,152. Okay, because I have two layers, such layers. Okay, 12,228 times 49,152, then 49,152 times 12,228. So I can multiply it by 2. And I have, of course, after each attention layer, I have a MLP as well, multi-layer perceptron as well. So I have 96 of these. Can give me the number? 115. Okay, so 115 billion. So we have MLP, the multi-layer perceptrons, as 115 billion. Okay, so now your architecture is like this. So you have input, you have an embedding layer, then you have multi-head attention, then you have multi-layer perceptron. This thing is multiplied with 96. Okay, it's repeated 96 times. That's your GPT-3 architecture. What do we want from GPT-3? What is GPT-3 used for? It's used for language modeling. So you want it to predict the next word. Okay, but at the output of this network so far, you have 12,228 dimensional vector. So how would you use this to give a probability distribution on 50,257 dimension space? You would have a fully connected layer. Okay, so you have an output layer. I'll call it output layer, which would be 12,228 dimension times 50,257 dimension, and this would again be 615 million parameters. 12,228 times 50 times 257. Okay, and that's essentially it. You will get a distribution on the next word. Probability of x of t given x of t minus 1 all the way till x1. So the GPT architecture that we, so that's all it is. We have accounted for essentially every parameter of this network. We know where it's used. Okay, now let's add all of our weights and let's see if we get the full thing. So 615 and 615, this is 1.230, okay, billion, and then we have 57, and then we have 115. Okay, so this is 12, 13, 7, and 1. So 173.230. I would say this is 175 billion. Okay, roughly 175 billion. Okay, so now we know GPT-3 architecture in and out. Okay, we know it completely. We know exactly what's going on. Everybody's with me? Okay. Now let's come back to some of the other concepts that we have in our thing. So we looked at input embedding, positional embedding, key query value, attention, self-attention, multi-head attention, feed forward, add and norm. Okay, this is a good thing, add and norm. So remember I'm doing everywhere. I was saying that output embedding would be input embedding plus delta E. I'm talking about multi-head attention. Okay, and this delta E, this is the chain that you have collected from all the previous words, previous tokens, and then over all the heads. So this thing can grow. Okay, this thing can grow. So what we typically do is after every multi-head attention layer, we normalize it. That's it. So you take the vector, you find the mean of it, you find the variance of it, and you say the vector minus mean of the vector divided by the variance of the vector. That's it. Okay, that's the, and by the way, why do we do this addition? Why is this addition a good thing? Because this provides a skip connection. Okay, so now you have a skip connection. Gradients, you can make it 1,000 layers and gradient would be able to flow back. It's a very neat, clean architecture. Okay, so we have this, we have done the encoder. Encoder, decoder is when you have, let's say, different languages. Now this is what is left, mask attention. So what is masked attention? So let's say I'm training a transformer network. Okay, I'm training a transformer network and I want it to. So I'm giving it a sentence. I am happy today as this is the last day of the class. Okay, I give this. Okay, now I'm training it. So I've given it the output as well. I'm setting up a loss function. Okay, and I'm doing attention. Now, if, for example, I'm at happy and I want to predict the next words, most definitely I should not be allowed to see the future words. Right? If I'm at happy and I'm allowed to see today, alas, I will output everything with 100% probability. I'll be able to do everything well. Okay. So how do I ensure that when you are at happy, you only look at what is in the history and you don't look at what is in the future? This is done with something called masked attention. So let's say I'll make this sentence a bit small, I'm sorry. And I'll just take 4 words. I am happy today. Okay. So if I do that, let me create the key query value pairs. So I have query for I have query for M, I have query for happy, and I have query for today. Similarly, I have key for I, key for M, key for happy, and key for today. Okay, and what is this? I just need the dot product of these two. Okay, of these vectors. Okay, so when I'm at query of I, okay, query of I, it can talk to key of I, right? Query of I, can it talk to key of M?
Yes.
No, because M is the future. Okay, you cannot see the future. So you shouldn't be allowed to talk to M. Okay, so I'm only allowed to talk up till here. Now query of M. Query of M, is it allowed to talk to key of I? Yes, because it's in the past. Query of M, is it allowed to talk to key of M? Yes, because it's in the past. So I am allowed up till here. Query of happy, is it allowed to talk to key of I? Yes. Query of happy, is it allowed to talk to key of M? Yes. Query of happy, is it allowed to talk to key of happy? Yes. Okay. And I'm going to do it for today as well. So I'm only interested in this part. Remember these dot products, they will go into a softmax layer. Okay. And at the output of softmax, I want the probability or the weight here to be 0, 0, 0, 0, 0, 0. So which number should I put here such that the output probability here should be 0? Can I put 0? Can I just make these zeros? No?
Directly without calculating, do some.
No, no, but see,
Zero. No, you can't make zero. You can't put them zero because you're talking about past. We're talking about past, not future.
Yes.
So
yes, but remember, in this matrix, I'm talking about the dot products of the key and query. So if I put the dot product of key and query as 0, will the softmax be 0 as well? So what should I put for the dot product so that I'm sure that the softmax is 0? Minus infinity. Okay, so you should put minus infinity here. When you put minus infinity here, the softmax of minus infinity would be 0. Okay. So what you put is minus infinity, minus infinity, minus infinity, minus infinity, minus infinity. This is mask retention. Okay. For decoder, you have to have mask retention because you're not allowed to see the future. For encoder, it's fine. You can have full attention. You can look at the future as well as the past because you are encoding it. Okay. Everybody's with me? Okay, let's see what else do we have. Encoder, decoder attention, I'm not going to talk too much about it. Okay, I would say we are good. The only thing which is left is the tokenization. So let's take a 10 minutes break. Let's just stretch our legs a little bit, then come. We'll talk about tokenization. Dua would do the character RNN Shakespeare notebook for you guys. And Mujtaba will do attention for you. And then Dua will walk us through a little bit about the homeworks. What are the outputs that we are expected for the homeworks? Okay, so 10 minutes, let's get back at 2 because we have a couple of things to do today. Guys, I announced it earlier in the class. You guys might have received a link for the course evaluation. Evaluate the course, it helps us make things better. Okay, so that should be in your email. You guys should have gotten an email. Do it. I want to get 75. Well, we don't have 75 people now. 67. 66. I want to see all 66 answers.
يا اخي هذا ما ادري من السبب الحين الدكتور اتوقع الدكتور يقول maybe تعطوا الوعي خلاص ولا ما في مشروع ايش يقولون انا صحيح انا ما حضرتش واقول فيها بثقه في البيوت ما كان يعطوني تفاصيل الموسيقى بدري اليوم المسألة طول السنة لازم اسمع مين شوف هذا مين هذا ما 75 مليون بس 100 مليون او كمان تغنى هذا شلون ما تدري وصفة لا ما يمكن اسمع شو بس أنا أدري إيش قاعدين الله أدري لا بدلعك والله العظيم
ما يبغى يقرأ.
كذا تقول لك خلاص ما يصير يجيب راسك الشغل انا شاوري انا موجود بالمركز الحكومي انا هذا السعوديه يا ابوي انا كلمت في العمل ما في شيء اسمه شبكه صوت المعلومات ولا مكلف على المركز الا العب شبكه ايش الوضع معي؟
تاخذ شعبة ولا ما تاخذ؟
انا ما ادري ايش يهمني نجاح بس يمكن لما في المكان
في انتماء
لا لا مو انتماء الموضوع بس في حاجه خلاص يقول يعجبني طريقه عملها او
بس انها تحسن خلاص اديت
بالضبط. طبعا الرياض عندنا شغال الى يومك هذا 4 سنوات 5 سنوات على السنه. كنت اول حديث حقوق موجوده في كل شيء. ليه؟ لان حاولت السكاجه كنت يوم وصلت مرحله الوضع خلاص طبقت اكتفيت من الموضوع. ما عندي بس في العالم ما زال تذكروا ذيك الايام بس انا اصلا شيء ذي
كم سنة
لكن
وضعت في الطاقة.
لكن وصلت مرحله الوضع بسبب اليوم صلنا الى والجدول اللي ما حتى انا نشتغل كل مقاطع من غير ذكر العمليات من غير خلينا كان هو 26 أداء طوال الإنسان يكون بالنور بكرة من الفجر بعد الفجر
تسلم الصالح.
وهو بالليل وتفكر 100 ساعة. طبعا بس تاخذ عربية هذا جزء 9 شوية.
دير بسعود.
لا قبل عربية بشغال.
لا بسنين دير بسعود.
لا خلاص اللي قلب
منو هي الكاتبة؟
خالد
قال راح يمرون.
مشكلة خالد هذا العيال خالد عوض
نفس هي
أبو سلوك وأبو فيصل. لا
أي طبعا.
لا طب شو
لا
سبعة ومستمع العملية ولي مستلمها.
أنا ثاني عندما واحد العملية كبيرة.
أنت بعد على طول.
أنا ما أتكلم لا لا أقسم بالله العلي العظيم لو استخدمت مراقي يا بس لا طويل ورقيا ورسميا ما في شيء رسمي. لو يمسحون المساهمة بتاعت البيانات وبعد استمرار ولا مستقبل ما مستقبل وأنا مساوي أنا شاب أنا بس قاعد أستغل طول السنة المسخرة اللي هم عايشين
يعني تستلم بعد
المفروض إيه بس لا أنا
يا شباب تسليم كان جروب
خلاص أوريدي قررنا الموضوع مش فاهم
ليش نداوم مخمس؟ ليش ندفع نستطيع
أقول 4 أيام بقى.
هذا الجروب
الله النقطة
أنت
اللي
كريتيكال بقى حبيبي. أنا إيش مكتوب قدامي؟
أنا أول كنت أعطيك معلومات صحيحة لكن
يعني مش ورا أي خطوة أكتبها الاثنين على سوي فيها.
إيه لو الحمام زاجي نص الجمهور
وهذا بروبوزل
بروبوزل بهذا الأسبوع الجاي.
قبل ما تروح الطالب السابع عشان بس تشوف الصورة كلمته وقلت له ما تبي بشر هو خلق
أنا شفت شو مسوي يعني كنت ناوي أجيب له حاجة
هو بنفسه قاعد يقول امشي هاي عقله يشتري بس
هو اخذ
شوف انا قلت لهم ساعتها لاعبني مواصفات في بيت طلب مني المواصفات اعطيته الوصف شوف يقول هذا الكيس لا هذا الكيس حق البي سي كم سعره؟ 7900 هذا كيس المبيت حق هذا بس كيس سعره
طيب
يوم اعطاني المواصفات دي خلاص تمام خلاص لا لا ابدا لا اخذت من موجود ايوه زبده شو اللي صار قال ابشر هذا بس هذا زبده بس
والمواصفات اللي انت كنت هو اخذها ولا مواصفات ثانيه؟
خلاص وش بدي انا اخذها من لو اخذت اعطوني المواصفات حقتي اللي كذا اخذها العسكرية
ولا لابتوب ولا
لا انا دي سي انا دي سي هو دي سي ما ينفع لانه ما فعل ما اقدر ادرب ومن بدي ادرب عليه وحتى السنه وصلت المنطقه الفعليه فين هذا مشكلة اللي يقول أنا ما مسوي
مجتبى مجتبى can we ask the guys to come in? Thank you very much.
والله ما مسوي كلام كذا والله اني كان ابراهيم ارسل في كلمه كان ابراهيم قبل التخصص هو رغم مخه اني انا اللي اسوي
من يكون يعني من يكون هو مسؤول
انا قلت له لا ما يتكلم ما ادري
لا والله
على الطبقة الجبرية اللي الناس تتوقع كذا ما راح تقطعها فشلنا نكون هذه
Okay, guys, so can somebody drop a message on the group that we are starting?
Yeah.
Thank you very much. Okay, guys, so let's start. Let's look at the last topic for today, which is tokenization. Okay, so the issue is that so far what we have looked at roughly is tokenization at word level. So each word is a token. The problem with language in general is that words frequency in language follow what is called a power rule. So the first word, or the second word would be present half of the frequency of the first word and so on. So which means that it has a long tail. So the number of words is fairly large, but the words are used not very frequently. They would be used infrequently. So we can do, for example, something like capping at 50,000 words and then saying that, okay, the rest of the words are, let's say, unknown characters or something like that. But we have some nice algorithms where we can do something better than that. And one of that such algorithm is BPE, which is byte pair encoding. Okay. Let me go to the other extreme. So I did encoding or tokenization at the level of words. What if I do tokenization at the level of characters? Okay. I can do tokenization at the level of characters. For English, I would just need 26 characters, and I would be able to write everything. What is the issue with this approach? Yeah, expensive because context lengths would be very large. Okay. And remember, the computation in transformer goes with square of the context length. Okay, because each word has to attend to each word. Okay. So if you have a context size of let's say 100, and it's taking, let's say, 10 minutes, if you make the context size 1,000, it would take 100 times more time. Okay, because computation it would be 100 times more expensive. Okay? So we don't want context size to be very large. So we have to be somewhere in the middle, where the dictionary size is not too large, and the context size is also not too large. So my question is that, let's say I take all the word in English language. Let's say these are 1 million words. Okay. So what would happen? The only additional expense that I would incur in my architecture is that this term would grow large, right? This term, if I have 1 million word, this term would go to somewhere, something like, 12 billion parameters, right? And this term would also go to 12 billion parameters. So this is roughly 24, about 1/8 of the parameters of the network. It's not terribly large. Why aren't we doing it? In terms of number of parameters, it does not incur a huge amount of loss. But what is the issue? The issue is that the final layer of your neural network is a softmax. Okay, softmax is a distribution over classes. If the number of elements in this class become very large, then this distribution can become very unstable. Okay, so distribution on 50,000. So you have 50,000 words, not 50,000. 50,000 numbers, all positive numbers which have to sum to 1. So you can see that it's a difficult distribution, but somewhat manageable. If this is 1 million characters, it would be very difficult, very unstable optimization problem. So we don't want the dictionary size to grow too much. Okay, so it has to be somehow contained.
Scaling method. You scale. It's still in the range of scaling.
No, but the thing is, it's not just scale. It's like these numbers, softmax, you have to do back propagation through it, right? So if these numbers are, let's say, not stable, then you cannot train anything. So softmax layer is the most important part of your network because it is giving you the probabilities of your output on which you are constructing your loss. If this layer is not, let's say, well suited, or if it's not giving, if it's unstable, let's put it that way, then you would not be able to learn much. Okay, so coming back to byte pair encoding, can we do something where the dictionary size is not terribly large? Okay, the dictionary size is also reasonable, and the context size is also reasonable. Okay, I'll give you an intuition. The intuition for this is that the words or the sequence of words which are repeated most, I would want to represent them with tokens. and the word sequence which are not very common, I would represent them with characters. This would essentially, on average, minimize my context length for a given dictionary size. So how do we define which words are more positive, which are more frequent, which are less frequent? An algorithm for this is byte pair encoding. So what you do is you essentially write your data. So I'm going to take an example where I have, let's say, characters. Okay, I have 4 characters, A, B, C, and D. Okay, so I would have sequence something like A, B, A, C, A, B, A, C, A, D, A, D, D, A. This is my sequence. Okay, I have a dictionary size of 4. I have a dictionary of A, B, C, and D. What I would do is I would look at the most frequent pair of characters in this pair. 2 words, 2 characters which are repeated the most. Okay, so let's see which one is repeated the most. So A is repeated once, A is repeated twice, A is repeated 3 times, and A is repeated 4 times. So A is probably repeated the most. So what I would do is I would say I would add a new token. AA would be E. Okay, so now your dictionary becomes A, B, C, D, E, and your sequence becomes E, B, A, C, E, B, A, C, E, D, A, D, D, E. You see, vocabulary size increased by 1, but the sequence size decreased by 4. Okay, now you repeat this process. So let's say the next common word I think probably is BA or CE. Okay, let me take CE. Okay, so CE, I'm going to represent it by F. So now you have A, B, C, D, E, and F, and this becomes E, A, C, E, I did, right? A, B, C, F, D, A, F, D, A, E. Okay, next I do B, A, S, G. Okay, so A, B, C, D, E, F, G. Okay, so B, A, S, G. So E, G, F, G, F, D, A, D, D, and so on. So whatever dictionary size you're given, let's say you are said that you are told that the dictionary size is to be 100. You can take it to 100 steps and decrease the context length. Okay. Now, tokenizations come with large language models. Okay, so you have a tokenization for text with GPT-3, GPT-4, GPT-4.5. Why wouldn't it be a great idea to use it, for example, for Arabic?
Motions?
No, just think purely from the perspective of tokenization. No, just purely from the context of tokenization, why it might not be a good idea to use the GPT-3, GPT-4 tokenization for Arabic text. Because
It's not only 27 letters. It's more.
Okay. So if you look at it, what is byte pair encoding working on? It's working on frequency, how frequent a word or a particular token is in the data. So the data that GPT-3 guys would have used, it would have been like 90% English and 10% other languages. So Arabic might be a small fraction of it. So what it would do is that Arabic, it would break it into small alphabets. Because we have seen that things which are not frequent, they are individual characters. So Arabic words, a reasonable size sentence might be broken into many small tokens. And then the context would be limited, you would not be able to learn much and so on. Okay. So ideally speaking, somebody should create a tokenization for Arabic. I have to check whether there is a good one or not. So if you just create it purely with Arabic data, then we would be able to use efficiently the Arabic text and we would be able to tokenize it. Okay. That's basically a high-level summary of the tokenization. So now essentially we have done all the concept related to transformers. We are all set to look at applications of large language models or transformers. So essentially we look at the full history of natural language processing from 50s, 60s all the way till 2010s when LSTM was at its peak to attention-based methods, which have been the state of the art in the last up till 7-8 years. Okay, so I'm going to hand it over to Mustafa to give us an example of attention. Okay, then Doa is going to walk us through a notebook on language modeling. And finally, Doa is going to explain a little bit about the homework. What are we expected to do in the homework for this week? Okay, good luck. What?
There's something called birth rate detectorizer. If it's high, then it means that the detectorizer is not doing well. And the context window is getting less because so too many tokens.
Too many, okay. Okay. Okay.
So it's a measurement
Our efficiency of tokenizer. Mustafa, you want to share a notebook with me? Or?
Yeah, I'll do that.
Yeah.
Right, so hello everyone. This is Mushtaba, and today I'm going to be talking about the Attention Implementation Lab. Dr. Naeem Allah already explained the mathematical foundations behind it and what it does, and now I'm going to be talking about the applications. And so, if we talk about attention implementation in the real world, so for example, say that you are talking to ChatGPT or Gemini, and sometimes you get surprised how it effectively understands what you are asking. It's basically because of the attention implementation. So basically, imagine that you are in a room and you are hearing a lot of noise, and suddenly someone shout out your name. You will filter out all the noise and you will look at this person. And this is basically what the attention does in the large language and in the ChatGPT and the AI models. So it makes it focus on the important parts from what it's given. Okay. So in this lab today, first of all, we're going to be looking at the softmax function, and we're going to do some visualization to see what it does and how it behaves. And after that, we'll take a look at the dot product attention. and then we're going to be doing some visualizations as well. And last of all, we're going to take a look at the PyTorch implementation. Okay. So so first of all, for the softmax, we're gonna begin with importing the libraries we want. We want the NumPy library as usual to deal with the data that we are giving. And we want the matplot to allow us to make the visualization and plot whatever we want to visualize. So after that, we're going to define the softmax actually. We're going to compute it along the specified axis that we want. And we're going to give it some inputs, which is X here in this case. So first of all, we're going to compute the exponential of the input value, because basically what the softmax does is that it takes the input of numbers and it converts it to probabilities to 0. So what we're doing is that we're going to sum along the axis because we want to normalize whatever the data we have. And then we're going to make the function return it to us. So basically, by dividing the exponential over the sum of the exponentials, then this is basically what the softmax function does. It basically normalizes the output and it gives us the probabilities. So, okay. So beginning with the visualization, what we're doing here is that we're using the linspace function. So we're gonna have a range of -5 and 5, as you can see here from the graph, -5 and 5, and we're gonna have 100 evenly spaced values in the graph. And then we're gonna apply the softmax to the input that we gave it. So we can see the probability on the y-axis, basically. So, okay. So we can look at the graph now. As you can see, there is kind of a trend here, actually. So beginning from -5 to 0, the curve is kind of stable, and it is small compared to the other area here. And the reason is that for the negative values and very small, for the negative values, the softmax assigns a very small probability for that. And you can imagine it. For example, if you have the exponential and the power is something negative, like -5, -10 or something, it outputs you a very small probability, such as 0.000 or something. So that's why we basically have some kind of similar trend here from -5 to 0. So after the 0 here, we have positive values, right? So we have the exponential that is so like exponential to the power of 1, exponential to the power of 2, 3, and so on. So basically, it's a larger probability for here, and that's why the curve really increase and sharp increase at the end, because as you go in the x-axis, the exponential increase is getting sharper and steep. Okay. So basically here it says what I just mentioned. And then now we're gonna take at the dot product attention. Okay. So basically in this, what we are looking for here is that this technique actually is used in models like transformers to help them focus on relevant parts of the input. So suppose that you have a large input and you have the attention, you want to focus on the things that are the most important to you. So that's basically what this technique does. And the fundamental idea is that each input, which is the query, computes a similarity score with other elements which are called keys, just as the doctor mentioned and explained. And the results actually are used to weight the values accordingly. That's why we have attention weights and attention values at the end. Okay, so going to the function here, to the computation, first of all, we are computing the similarity score. So by multiplying the query by the key transpose, we can compute the similarity score in this case. And the reason Why we are doing the transpose is that we want to maintain the dimension that we want to do in this case. And after we do that, we want to convert the scores to probabilities. And then we will rate the values by attention scores. The higher the attention score, the more focus on the segment will be. And then this function will return to us at the end the attended values and weights. Okay. So basically, the attended weights, it shows how much focus each query element gives to the different parts of the input, and the attended values gives us the weighted sum of the values based on the attention scores that we are given. All right. So moving on. So here we're kind of doing a matrix here, a random matrix that has the dimension of 128 by 128. And then we are assigning key and value matrices initialized ones. So basically we have the key value pairs here of ones that we are assigning. And then for this line, we just have it just in case. It's just the purpose of it is actually to set the last column to 0 in case we want to do that. And so after that, we want to compute the attention values and weights. So we have the attention values here as our output and the attention weights here as another output. So two outputs in this case. And we have the dot product attention, dot product attention of the query by the key value. And the reason why we have the key value here twice is that we want both outputs here to be the same size. It's very important. So after that, we are actually plotting the results. So as you can see here, we are creating subplots. There is the original value plot and the attention weights and the attended value. And basically in this line, we did it to assign the titles for each subplot that we want. And then we will do a loop here, a for loop, actually, to display us with the matrix with the heat map. So each one is a heat map that represents some meanings. So for example, the first one here, this is the original key value pair. And the reason why it's black, actually, because it consists of all ones. The matrix has all ones. So there is no variation in the value, and that's why it is then black. There is no variation of the color. The same tone, the same color, the same everything. And for the attention weights here, we have some kind of horizontal stripes, actually, varying in color, and this represents the similarity that we computed previously. So the brighter the color, the more similarity we have, and the darker the less. And then we have here the attended values, actually, and it has some kind of similar trend to the attention weights. It has stripes varying color, both red and black. So basically, it demonstrates the attended values that we have already computed. Let me check if I missed anything here. So basically, the takeaway here from this part is that actually the implementation of the dot product attention selectively enhances the relevant information, but it's suppressing the less important details. So more important details are demonstrated, and we focus on them, and the less important details, we just ignore them to make the model work more effectively. And as we mentioned in the beginning, just like the example about ChatGPT, when you give it a whole bunch of text and paragraph, it does not want to focus on all of it, because it will focus on all of it, of course, but it will focus more on the goal of the question that you are asking, and it will give you the output the desired output that you want to hear or you want to obtain the answer about. Okay. So now moving on, there is the PyTorch implementation. So in the second part, we've seen that the dot product attention works mathematically. Now we're going to implement it in PyTorch. So in this case, the main difference is that we're going to use learnable parameters instead of manually inputting every input we want. We'll just do it by the learnable parameters. So this will be faster for us and easier. And as you can see here, we're beginning by importing the libraries actually. And then we are defining the class that we want. And we have the init module. Basically, it inherits the PyTorch, so it allows us to use it. And then we are going to initialize the attention mechanism here in this case. So, and we are giving it two inputs, self, to give us access to the attributes and the instances of the objects that we have, and the embedding length to give us the size of the embedding for the query, key, and the value. Oh yeah, of course. Is it better now? Good. And then after that, we are using the function super, basically its parent class constructor. And we are defining the linear transformation for the query and the key and value. So as we did in the RNN layer to get the attributions, we are doing it here again. We're having in linear, and it's taking the input, which is the embedding length. And basically the reason why we have the input kind of appearing twice here is that we want to maintain the same size of the input and the output as well. And so we're doing it 3 times, one for the query and one for the key and one for the value. So after that, we will do a forward pass in this case, and it will have several inputs. First one is self, second one is query, and third one is key, and the fourth one is value. And this is basically, we are doing it to compute the attention in this case. So our input tensors that we mentioned earlier, we are using them to compute the attention. Okay. So after all of this, we are applying linear transformation to the Q and K and V. We are transforming each parameter that we have to allow us to use it. And then we are computing the attention scores using the matrix multiplication, which is the dot product in this case. So basically, the reason why we are doing the transpose is that we want the dimension to match the matrix multiplication, because if it doesn't, we will have a lot of problems and a lot of errors, and we want to avoid that from the beginning. So then we will apply the softmax to get the attention weights. It's basically the normalized importance of each key. So we look at each key and we see how important it is to us and how much focus we want to give to it. And then we assign it. And then we compute the attended values by weighting the value matrix with the attention weights. And then at the end of this, it will return us the weighted values and the attention score that we want. So I guess maybe here two key takeaways in this case. The previous implementation that we did, which is the dot product, in this version, it allows the attention mechanism to learn optimal transformation for a query. So basically, by using the PyTorch, we have learnable parameters that makes our work way much easier. And then another takeaway is that the training in this module on data, the module automatically actually adjusts the attention scores. So it constantly updates the attention score and gives it to us. So this basically improves the performance in complex tasks in NLP. So yeah. So I guess that sums up what we have in the attention implementation lab. It's a fairly short lab compared to yesterday's. So yeah, that's about it. Thank you so much. Yeah, Duana will explain actually the Shakespeare lab, which is basically about the is going to talk about the RNN again, but some kind of different structure, maybe architecture. Right, I finished. If you want to come.
نفسه دكتور شكله فتحها وين وراه attention emotion Shakespeare عشان اسمعوا عشان يسمعوا صوت واضح؟ أمس أخذت RNN أو قبل أمس تقريبا مع دكتور نعيم. RNN نيورال نتورك تتذكر إيش الأشياء السابقة اللي صارت. طيب فالحين راح نسوي لها implementation على داتا سيت اسمها شكسبير، اسمها شكسبير تكست. تمام. فأول شيء راح أسوي خلاص ماني سامعة. It is recording. هي recording.
يقول بعد سووا ريكورد نايم وأول واحد جالس نايم
بس عندهم موجودين.
Is it better now? طيب ممكن يعني أنا عارفة أنتوا صامين تعبانين بس ركز شوية أشرحها بسرعة يعني. طيب شكسبير داتا سيت عبارة عن تكست سترينج واحد. طيب يعني أنا في واحد سوى كوتيشن مارك كتب شكسبير كامل بعدين كوتيشن مارك ثاني، فهي عبارة عن سترينج كبير كامل. طيب زي لما نكتب مثلا برنت هلو وورد نطبع برنت، شكسبير نفس الشيء واحد سترينج بس. طيب فأنا أول شيء بسويه لازم أعرف إيش الفوكابلري حقتي في شكسبير اللي هي الحروف. أنا أبغى أعرف الحروف الموجودة لأن أنا هنا راح أستخدم ال RNN هذه عشان ما راح أسوي prediction لورد راح أسوي كاركتر يعني أشوف مثلا إيش الكاركتر ممكن يجي بعد هذه الكلمة وهكذا لين ما أكون كلمات. طيب فأنا أول شيء راح أعطي شكسبير تكست في ست. ليش ست؟ طيب صح. بعدين حولتها ليست عشان أقدر أسوي لها دايركت أكسس، أستخدم الاندسيس حقتها. طيب بعدين سويت لها sorted. ليش sorted؟ لما الست ما هي مرتبة، فكل مرة أنا أسوي run time عفوا كل مرة أسوي run راح تتغير ترتيب الست، فراح يتغير الرقم. لو لما أسوي لها هنا بعدين أرقمها راح يتغير رقم لكل حرف. يعني مثلا ممكن A يكون 10، لما أسوي run time مرة ثانية ممكن يكون 20. أنا ما أبغى هذا الشيء، أبغاه دائما يكون نفس الشيء، عشان كذا أنا سويت لها sorted. تمام. بعدين أنا سويت هنا أبغى أعرف الفوكابلري سايز حقي كم. طيب أبغاكم ليش 65 كاركتر؟ أيوة في علامات الترقيم، وحسب الكاركترز السمول غير عن الكابيتال، فال كابيتال يعملها غير عن ال سمول. تمام. بعدين هنا أنا بس راح أسوي كالعادة الكاركترز حقتي راح أحولها أرقام. يعني ال A 0 مثلا ال B 1 وهكذا، راح يبدأ من 0. ليش استخدمت enumerate؟ عشان الليست عندها enumerate تعطيني خاصية في الليست إنها تعطيني indexes ضمنيا، يعني أنا مو مضطرة إني أسويها manually. تمام. ولكن عشان أبغى أخزنها عندي في دايركشنري ديكشنري عفوا، أو أخزنها في ديكشنري، فأبغى أسوي لها extraction من الانيموريت هذه. تمام. نفس الشيء هنا، بس العكس إنه الرقم صار قدامه حرف. طيب أنا الحين سويت الفوكابلر حقي، وعندي mapping characters to indices و indices to characters. التكست هذه حقت شكسبير أبغى كلها أحولها لأرقام، عشان النيورال نتورك حقتي ما تقبل إلا أرقام، ما تقبل الحروف. طيب. هذا عدد الكاركترز اللي عندي في شكسبير. تمام. الحين أنا راح أسوي الشكسبير داتا سيت عشان أضبطها الموديل حقي. تمام. أول شيء أنا عندي الانكود التكست حقتي اللي هي أنا سويتها توي هنا. الشكسبير داتا سيت كلها حولتها الأرقام، فأنا راح أعطيها لهذه الفانكشن. وهنا السيكونس لين حقي. السيكونس لين إيش يعني؟ إنه أنا الكاركترز كم كاركتر أبغى أعطي للموديل. يعني مثلا قلت له خذ 100 كاركتر، يعني كل مرة راح ياخذ 100 كاركتر يتدرب عليها، بعدين 100 حسب الإيبوكس حقتي. هنا ريتيرن 5000 النمبر of samples per epoch، يعني راح ياخذ من التكست حقتي 100 5000 سامبل طولها 100 في الإيبوك الواحد. تمام. طيب هنا إيش راح أسوي؟ أنا مثلا حددت له 100. أنا هذا راندوم سامبلينج، راح أقول أنا راح أختار الإندكس حق البداية من 0 إلى هذه الكاركترز حقتي كاملة أنقصها من السيكونس حقي. مثلا السيكونس حقي كان 200، راح أنقص منها 200. طيب فراح أقول إن أنا مثلا راح آخذ من 0 إلى العدد اللي طلع لي بعد ما سويت الطرح. طيب والإندكس حقي راح يكون الجمع. عموما يعني هذا إيش تسوي؟ تعطيني 100 كاركتر أو 200 كاركتر أو 500 كاركتر اللي أنا قلت له أنا أبغاها. طيب وهنا أنا أحولها لتنزر، لأن النيورال نتورك تحتاج تنزر عشان تشتغل. طبعا هنا ناديت الداتا سيت حقتي الكلاس اللي هنا سويته، أرسلت له الانكود التكست حقتي وقلت له إن السيكونس حق اللينث 200، والباتشز عندي 64، والترين لودر عشان يسوي لي شفلينج ويسوي هذه الأشياء أوتوماتيكلي وأنا ما أضطر أسويها مانيوالي. يعني الترين داتا سيت اللي هي هذه. والباتش سايز 64 وشفلينج ترو إنه أنا أبغى لي ما أبغى الداتا سيت حقتي دائما تكون نفس الترتيب فغير اللي هي. طيب الحين هنا ال RNN عندي 4 layers. أول layer لا 3 هنا 3. طيب عندي الهيدن سايز اللي هو كم هيدن ستيت أنا أبغى. النمبر اوف لايرز أنا كم لاير أبغى في هذه ال RNN. والإمبيدد اللي هي الإمبيدد لاير اللي هو أول لاير عندي في ال RNN تاخذ الإنبوت تحول اللي هو ل embedding vector space عشان أقدر أتعلم منها. بعدين هنا راح يسوي لي ال RNN الهيدن سايز حقتي اللي هو كم هيدن ستيت أنا أبغى كم هيدن نيورون أنا أبغى. والنمبر اوف لاير كم لاير أنا أبغى. والباتش فيرست شو إنه هنا أعطاني كل الباتشز لا تسحب على باتش واحد. بعدين الفولي كونكتد لاير اللي هي الاوتبوت لاير تاخذ الهيدن الاوتبوت حقت الهيدن ستيتس وتوجد لي الاوتبوت حقي بناء على مثلا لو ابغى كلاسيفيكيشن هي راح تسوي كلاسيفيكيشن لو ابغى جنريشن هي راح تسوي جنريشن وهكذا. هذا الفورورد باس. اول شيء انا هذه الانبوت حقتي الانبوت راح اعطيها للامبيدد لاير. الامبيدد لاير راح تسوي لي الفيكتورايزيشن سبيس. بعدين الاوتبوت والهيدن انا راح اعطي الار ان ان الامبيدد حق الفيكتورز حقت الامبيدد والهيدن. الار ان ان كل تايم ستيب راح تعطيني اوتبوت صح. راح تخزنها في هذا المتغير. طيب بعدين انا الاوتبوت عشان اقدر اوجد منه اوتبوت حقيقي زي ما انا ابغى لازم اسوي له ريشيب عشان اقدر بعدين استخدمه في الفولي كونكتد لاير اللي هي هنا. بعدين هنا راح يعطيني الاوتبوت حقتي والهيدن ستيتس. طيب هنا بس قاعد أسوي initialization للhidden state حقتي بناء على number of layers كم. مثلا لو قلت له 3 يعني أحط 3. الباتش سايز 64 والhidden states مثلا لو قلت له 128 راح أحطها 128. فهذا الhidden حقتي هذا السايز حقها راح يكون زي كذا. هو طبعا راح تكون زيروز. طيب فأنا هنا قلت له الهيدن سايز حقي 256 يعني أنا عندي 256 نيورون. النمبر اوف لايرز 3 والنمبر اوف ايبوكس 200 والليرنينج لايت حقي 5 في 10 والسالب 4. وهنا أنا حددت له إنه استخدم الجي بي يو إذا كان في جي بي يو لو ما في حيستخدم السي بي يو. طبعا هنا أرسلت له الفوكابلري حقي الفوكابلري سايز اللي أوجدته هنا هذا. بعدين أعطيته الهيدن سايز عندي 256 والنمبر اوف لايرز 3. أرسلت له يعني قلت له لو في جي بي يو استخدمها على الجي بي يو لو ما في استخدمها على السي بي يو. استخدمت الكروس انتروبي لوس والاوبتمايزر حقي كان آدم. هنا بعدين سويت ليست ترين لوس الترين. أبغى أعرف يعني كم الترين حقي كيف اللوس حق الترين كيف شكله يعني هل يزيد ينقص عشان أسوي له بلوت بعدين. وهنا أنا قلت له موديل دوت ترين يعني إنه هو الحين يحط الموديل في حالة التريننج وهنا يعطي الموديل للجهاز أنا حددت له جي بي يو. طبعا هنا فعلا راح أسوي التريننج حقي. الهيدن ستيت حقتي أول شيء لازم أسوي لها initialization اللي هي فوق هنا. أول شيء خليتها بزيروز. طيب هذا الباتش سايز حقي ليش ما قلت لها الباتش سايز تبدأ من 64 لأنه أحيانا عدد السامبلز ما يكون divisible by 64 فممكن أحيانا آخر واحد يكون 16 فما أبغاها تطنش خلاص تاخذه. بعدين هنا راح أعطيها الانبوتس والتارجتس. الانبوتس حقتي راح تكون كل شيء ما عدا آخر كولوم لأن آخر كولوم فيه التارجتس. والتارجتس راح يكون بس آخر كولوم عشان هو في التارجتس اللي أنا أبغاها. بعدين راح أعطيها للديفايس حقي اللي هو يعني لو جي بي يو حيستخدم الجي بي يو. هنا أرسلت الموديل حقي أعطيته الانبوتس اللي أنا وجدتها هنا والهيدن اللي هي هذه. في البداية راح تكون كلها أصفار بعدين راح تبدأ تتعبى على الإيبوك حقي. بعدين راح يعطيني الأوتبوت والهيدن الجديدة. كل مرة الهيدن تتغير عندي بناء على التايم ستيب حقتي. بعدين هنا راح أوجد اللوس حقي، راح أعطيه الأوتبوت والتارجت، راح أسوي لها ريشيب عشان أقدر أو أطرح. وهذه أنا أستخدمها، أقول له optimizer.0grad إنه بعد كل إيبوك أنا ما أبغى يستخدم الجرادينت القديم، لازم يحسب واحد جديد. بعدين هنا list it backward، هنا راح يحسب الجرادينت ويبدأ يعدل على الموديل حقي على الويتس، وهنا راح يعدل الويتس فعليا. هنا بس راح يحسب، هنا راح يعدل على الويتس، وهنا فقط يعني راح يطبع لي إيش قاعد يصير في الإيبوك اللي هو هذا اللي تحت. مفروض أيوة. أيوة. أسوي له رن الحين عشان تحت أقدر أستخدمه. طيب المهم التريننج حقي راح يكون زي كذا. في البداية راح يكون مرة عالي، بعدين يبدأ ينزل لأنه قاعد يتعلم، فاللوسس قاعدة تنقص. طيب
صار صار ما يتغير كثير.
أيوة لأنه راح يوصل لمرحلة إنه راح يعلق في المينيمم. المينيمم صحيح كذا جاية، فراح ما راح يقدر يطلع منه.
وهذا الشيء مطلوب يعني طيب يوصل منه.
هو الصدق إنه في حالات مو دائما، وإحنا نبغاه يوصل المينيمم. أه؟
بس هو
أيوة ممكن، ولها طريقة حل ثانية، إنه كيف تخرجه من المينيمم هذا توديه على المينيمم الثانية مثلا.
ممكن تسوي initialization مختلف.
أيوة وفي شيء اسمه adapting learning rate، إنه learning rate يتعلموا في نفس الموديل حقك. يعني learning rate إحنا بالعادة نعطيه جاهز في البداية، بس ما راح ينفع في كل الأحوال لأنه راح يعلق في مينيما لوكال مينيما، أنا أبغاه يوصل للجلوبال مينيما.
بس ممكن احنا بعد اذا وصلنا الى القصه اللي نسوي كابتشر للبارامترز اللي في الانبوت هذا، اذا طلع منها ما يرجع.
صح. وعموما لازم تحفظ تشيك بوينتس طبعا. أيوة. طيب هنا ما أعرف ليش حول الموديل للسي بي يو صراحة، بس إنه حول السي بي يو. المهم ما علينا. أنا الحين قاعدة أسوي تيستينج للموديل، أبغى أسوي له generating لتكست. طيب فأنا كيف أقول أسوي generate؟ إنه أعطيه حالة إنه أسوي موديل دوت ايفال. هنا راح يقول إنه أوكي أنا خلاص ما راح أتدرب، أنا راح أستخدم الويتس اللي لقيتها وقت التدريب عشان أقدر أسوي generation. طيب بعدين الهيدن حقتي راح أسوي لها initialization نفس فوق، بس هنا اخترت واحد. ليش واحد؟ لأنه أنا راح أسوي generation لكاركتر ما هي word. يعني كل مرة مثلا أول مرة A سويت generation، بعدين بعده B مثلا، على حسب الكلمة اللي عندي اللي راح أسوي لها generation. هنا حولت الانبوت حقي لأرقام كالعادة، بعدين قلت له with start no grade، إنه أنا ما أبغاك تحسب الجريدينت، أنت ما قاعد تتدرب، أنا أبغاك تستخدم الجريدينت الويتس اللي لقيتها من أول عشان نشوف هل هو فعلا كويس ولا لا. اوكي الجنريتد string انا هنا راح ارسل له string مثلا ذا، هنا راح يحط ذا. طيب فراح ارسل للموديل الانبوت حقي اللي هي هذه فيها كلمة ذا مثلا، والهيدن ستيتس حقتي، وراح يرسل لي الاوتبوت والهيدن اللي كل شوي قاعد تتغير. هنا انا راح استخدم الشار اندكس. ليش استخدمتها؟ انا الان الموديل اخر hidden state راح يعطيني هي تقريبا هي اللي فيها الديتكشن الجنريشن حقي اللي. طيب فأنا أبغى آخر هذا اللي هو -1 مثلا، ممكن يعطيني array فيها 0.6 0.7 3.5. argmax راح تاخذ أكبر واحد فيهم اللي هو أعلى احتمالية أن يكون هذا الحرف مثلا. بعدين أنا راح أشوف هذا الحرف إيش الاندكس حقه وأحوله من الاندكس تو كاركتر. تمام. وهنا راح يبدأ يسوي generation letter by letter. مثلا أبغى أسوي generation لكلمة word راح يقول W، بعدين يسوي مرة ثانية يقول O، خليها مع بعض لين ما يوقف، لين ما أنا أعطيه مثلا sequence معين 100 راح يوقف عند 100. مثلا هنا قلت له is th، أرسلت له كل شيء، فهنا بدأ من is th وراح يوقف عند 1000 لما يوصل لين 1000 كاركتر. اوكي هنا قلت له يبدأ من سبيس، وراح يبدأ من أول سبيس يشوفها مثلا إلى الكاركتر 3000. واضح اللاب؟
تقيم التكست هذا هو كويس ولا لا؟ كان في طريقة غير إنه يعني هم يقرأ؟
صدق ما أدري. هنا دكتور نعيم. How do we know if the generation was good or not? Based on what? قول في ماتريكس نستخدمها اسمها complexity مدري ايش اسمها. Do you have the homework here? Didn't send it yet.
Didn't?
I will send it now.
شوي مهارات لياقة أشياء كثيرة. ها؟
أصفر ولا جوجل إيش؟
ودك تشارك صح؟ دورة أي محتوى غير يعني شارك
Oh my God.
لا غير انت بالنيتر عليك بالنيتر عليك لا الرحمن شافي من الرياض بس الأمان كان هو أفضل عين. إيه لو كانوا عينة
طيب الواجب راح يكون عندكم أربع واجبات. أول واحد راح يكون text classification. راح تستخدموا الداتا ست اسمها 20 news group data set. هذه فيها جرايد، مقالات جرايد، وعبارة عن تكست فايل، والعنوان حق التكست فايل هو الليبل. طيب انتوا بس راح تستخدموا 5 كلاسات من أصل 20 كلاس. أول شيء راح تسووه إنه تسووا بري بروسيسد الداتا. لو كانت مثلا تخلوها كلها lower case أو upper case، تشيلون الستوب وورد، تشيلون علامات ترقيم، تسوونها stemming وهكذا. بعدين راح تسووا TF-IDF ماتريكس للترين والتست داتا. وتكون الماكس فيتشر 5000 عشان ما احنا ما نبغى نستخدم كل الفوكابلر اللي عندنا. بعدها راح تستخدموا النايف بيز موديل. هذا تقريبا تحلل نفس اللاب اللي شرحته حق TF-IDF الفروم سكراتش. تمام. راح تسووا النايف بيز عشان تشوفوا على تسووا يعني على الداتا تدربوا عليها وتسووا لها evaluation. بعدين هنا راح تبدأ تسوي نيورال نتورك. واو. طيب بعدين راح تسوي نيورال نتورك 2 layers simple نيورال نتورك، وتستخدموا فيها TF-IDF اللي أوجدتوها، تسوي توكنايزيشن للداتا طبعا. بعدين راح تسوي RNN GRU LSTM. وآخر شيء راح تشوفوا البرفورمانس، تكتبوا يعني أي واحدة performance حقها أحسن ولا إيش، باستخدام الكونفيوجن ماتريسيز. شو هي جاهزة لكم يعني، انتوا بس اعطون اللودينج جاهز، انتوا بس راح تسووا بقية الخطوات. واضح تسوون؟ هو 4 واجبات 4 files. اوكي. طيب هنا ايش راح تسوون؟ في داتا ست اسمها كوكا عبارة عن صور، الليبل حقها الصورة نفسها. مثلا ممكن يكون صورة كرسي مكتوب chair مثلا. فانتوا ايش راح تسوون؟ راح تستخدمون 2 موديلز. اول موديل راح يكون للبيكتشرز زي مثلا ريزنت راح تسوي فيتشر extractions للفيتشرز الموجودة في هذه الصورة. تمام. بعدين الفيتشرز هذه المفروض ندخلها في NLP موديل. ال NLP موديل المفروض يعرف هذه الصورة إيش فيها. مثلا لو فيها طاولة المفروض يكتب طاولة أو يكتب عنها وصف. هذه فكرة الهومورك حقكم. إيش الستبز اللي تتبعوها؟ راح تسوون أول شيء pre processing الداتا، tokenization، توجدون الفوكابلري، ولازم تضيفون SOS و EOS لأنه هو راح يسوي generation. لازم يعرف بالضبط من متى يبدأ ومتى ينتهي. بعدين لازم تسوون padding للداتا عشان تخلونها كلها نفس الحجم. لو مثلا كان أطول واحد عندكم، مثلا أطول تكست عندكم 100، المفروض كلها تكون 100 عشان ما يسبب مشاكل وقت التدريب. بعدين تسوي splitting للداتا، 90% منها يكون training و10% testing. بعدها راح تبدون تسوون الإيمج انكودر اللي هو الريزنت. ممكن تستخدمون ريزنت يعني. راح تسوون الكودينج حق هذا الانكودر بحيث انه ياخذ بيكتشر، بعدين يعطيكم فيتشرز حقت هذا البيكتشر. بعدها راح تسوون RNN LSTM و GRU decoder اللي هو هذا عشان ياخذ الفيتشرز حقت البيكتشر ويوجد أو يعطيك وصف عنه. بس كمان خلينا نتأكد. أوكي. طبعا لازم تسوي combining عشان بحيث إنه يكون في seamless integration بين الاثنين. على طول تعطيه صورة وهو يعطيك الكابشن حقها. بعدين راح تسوي evaluation للموديل حقتكم بناء على هذا السكور. بعدين راح تسوون من التست ست راح تسوون generation ل 3 pictures عشان تشوفون ايش الكابشن راح يعطيكم هنا. تكلم يا دكتور نعم. اوكي طيب والله ما ادري ما
هذا مشروع
طيب ثالث واجب راح تسوون answering question answering bot. راح تستخدمون داتا set اسمها Grade School Math 8K QA اللي هي فيها أسئلة رياضيات وكل question له إجابة. مثلا 5 apples plus 2 apples كم راح يعطيك؟ هذا الquestion المفروض البوت يجاوب كم؟ 7. فأول شيء راح تسوونه كالعادة pre-processing للداتا tokenize the data. راح تستخدموا sentence pieces والبارامترز حقتها راح تخلونها زي كذا إنه أنت تبغون الفوكابلري سايز 1000 الباد اي دي 0 unknown ID هذه إنه أي كلمة ما هي موجودة في الفوكابلري راح يخليها 0 أو 1. المهم إنه راح يسحب عليها. بعدين هنا راح يخلي ال beginning of sentence وهذا ال end of sentence. تمام. طبعا لازم تضيفون SOS و EOS. بعدها راح تسوون padding لل source and target data يعني ال questions وال answers. وراح تقرؤون الداتا من CSV files. هي 4 files أعتقد. أيوة 4 files. فإما إنكم تستخدمون هذه إما هذه وقت التريننج. طيب وبعدين راح تسوون LSTM based على questions والمفروض إنه بعدين تصير جواب على الأنسرز. هذا الاركتكتشر عشان يساعدكم في الحل. آخر واجب طيب هذا اللاب راح تستخدمون اللغة العربية فيه. راح أعطيكم داتا سيت فيها أشعار عربية والمفروض إن تسوي جنريشن لأشعار عربية بناء على الأشياء اللي تعلمها. طيب أيوة يعني تعلم القافية وهالأشياء. أول شيء راح تسوونه مكتوب هنا راح تستخدمون RNN تبنونها from scratch. أول شيء راح تقرؤون الداتا من CSV فايل. بعدها راح تسوون pre-processing تشيلون أي non-Arabic characters ولكن لازم تخلون هذه الأشياء الوايت سبيس فاصلة نقطة علامة الاستفهام علامة التعجب والأقواس هذه لازم تبقى يعني لا تشيلونها. راح تسوون print للtotal number of characters بعدين تسوون create للفوكابلري في الداتا set وتسوون mapping للورد يعني من word to index ومن index لورد. بعدها راح تسوون sequence length وتسوون create ل suitable dataset class بناء على الداتا set حقتكم. بعدها راح تسوون RNN وتحفظون التشيك بوينتس يعني بعد كل ايبوك المفروض تحفظون التشيك بوينتس هذه إنه هذا الايبوك ايش الويت كانت حقته. طيب هذه مهمة دقق عليها كثير. بعدين هتسوي
تجينا هذه اللي ترفعها بتصير كبيرة على البلاك بورد تشيك بوينت أنا
أوكي.
أفضل إن نحط الأحسن مثلا أو
آخر واحد.
طب نتكلم.
ترى جربنا ترى قبل كان سبب لنا مشكلة في مادة ثانية. بوينتس كبيرة مرة.
طيب تمام نتكلم إن شاء الله. بعدين أوكي راح تسوون فانكشن، هذه الفانكشن تسوي جنريت بناء على الار ان حقكم، يعني تسوي جنريت للشعر. طيب بعدها يعني انتوا راح تحفظون التشيك بوينتس، فالمفروض تسوون فانكشن تسوي لودينج لهذا التشيك بوينتس. اخر فانكشن راح تسووا لها انه انتوا راح تعطونه اسم شاعر، المفروض يعطيكم شعر generating بناء على